Have you ever looked up at the night sky, that velvet blackness dotted with diamonds, and wondered, where does it all end? Is there a wall at the edge of the universe? A final shore to the cosmic ocean? Or does it just stop? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. It's a question that whispers from the deepest parts of us, a curiosity baked into our DNA. We live in a world of boundaries and horizons, of beginnings and endings. So, surely the universe itself must have one. But what if the answer is far stranger, more profound, and oddly more peaceful than a simple edge? Join us on a calm journey to the ultimate boundary. We won't be traveling at impossible speeds, but drifting peacefully through the grand, silent theater of the cosmos. Our trip will take us from our familiar home, past glittering cities of stars and ghostly veils of nebulae, past entire nations of galaxies, until we arrive at the silent, unknowable expanse from which light itself may never reach us. This is a journey to the edge of everything, and into the heart of a gentle, pervasive nothingness. The first step is the biggest. Our journey begins right here. On a small, rocky world, drenched in water and wrapped in a fragile blanket of air. Our Earth. From our perspective, it's everything. The stage for all of human history, the source of every joy and sorrow we've ever known. Its diameter is nearly 13,000 kilometers, a distance that feels immense. But on the scale of our journey, it's less than a single grain of sand on an endless beach. Let's begin to float upwards, gently. The world unfolds below. Cities become grids of light, continents take their familiar shapes, and the curve of the Earth becomes undeniable. Soon, that curve closes on itself. Our home is now a perfect sphere, a swirl of blue, white, and green, hanging in the profound black of space. There's no sound here, just the quiet hum of our own existence. We drift past the moon, our silent, cratered companion, swinging around our planet with a clockwork grace that has governed our tides and inspired our myths for millennia. From here, Earth is a brilliant blue marble, and the Sun is a star of blinding intensity. Its light, taking just over 8 minutes to cross the vacuum and warm our world, is the engine of life. But we're leaving it behind. We're now moving with the thought. The inner planets Mercury, Venus, our Earth, and Mars fall away like pebbles tossed in a pond. We glide through the asteroid belt, a sparse ring of rock and ice, the rubble left over from the birth of our solar system. These aren't the crowded danger zones from science fiction, but lonely islands of rock separated by millions of kilometers of empty space. Past the gas giants we go. Jupiter, a colossal ball of swirling storms, a failed star whose immense gravity shepherds a family of moons. Saturn, with its impossibly delicate rings, a celestial jewel that has captured the human imagination like no other. Then the ice giants, Uranus and Neptune, distant and cold, lonely sentinels in the deep outer dark. Each of these worlds is a universe in itself, with its own character and secrets. But they're just the first few footsteps on our path. Our solar system doesn't end here. We have to travel much, much farther, to a place of myth and theory. We are entering the Oort cloud. This is a vast, theoretical sphere of trillions of icy bodies, loosely bound to our Sun. It's the source of the long-period comets that occasionally visit our inner solar system. We're now so far out that the Sun is just another star, albeit the brightest one in the sky. The scale here is staggering. This cloud is thought to be immense, stretching out over 2, maybe even 3 light years in diameter. We've spent all this time traveling, and we still haven't left our own backyard. Into the galactic sea. To continue, we need a new ruler. The kilometer has become laughably small. we have to start thinking in light years. And a light year isn't a measure of time, but of distance. It's how far a beam of light travels in a single year, about 9.5 trillion kilometers. It's a measurement handed to us by the cosmos itself, the ultimate speed limit. Our solar system is just a speck of dust in a vast ocean of emptiness. The nearest star system to our own is Proxima Centauri, over 4 light years away. 4 years, traveling at the speed of light. On our calm journey, we simply arrive. We see a small, dim red dwarf star, very different from our own sun, with its own family of planets. We're no longer home, but we're still in the neighborhood. This neighborhood is the Milky Way galaxy. It's a colossal, sprawling city of stars. Let's pull back, further and further, until we can see its full form. It's a breathtaking spiral, a pinwheel of light and dust, 100,000 light years across. It contains somewhere between 100 and 400 billion stars. 400 billion points of light, and for all we know, a great many of them have their own planets, their own stories. Our sun is just one of them, tucked away in a quiet, suburban spiral arm about 2/3 of the way out from the galactic center. From this vantage point, we can see the grand structure. The luminous central bar, a dense cluster of older, yellowish stars. The sweeping spiral arms, buzzing with active star formation, full of bright young blue stars and glowing pink clouds of hydrogen where new suns and worlds are being born right now. And at the very heart of it all, a gravitational monster. Sagittarius A*, a supermassive black hole with the mass of 4 million suns. It doesn't shine. It's a point of perfect blackness, a drain in the fabric of space-time around which our entire galaxy revolves. We'll spend a moment here, in the intergalactic space just outside our Milky Way, just to take it all in. 100,000 light years. If you imagined the galaxy was the size of North America, our entire solar system, out to the edge of that huge Oort cloud, would be about the size of a coffee cup. Every single star you see from Earth is part of this structure. They're our closest, brightest neighbors. But now, we must leave them all behind. Our journey is taking us to a place where entire galaxies are just points of light. The Laniakea supercluster, our cosmic home address. As we drift away from the Milky Way, it shrinks behind us, its beautiful spiral arms merging into a single lens of light. We're now in what's known as the local group. It's a small, gravitationally bound collection of more than 50 galaxies. Our Milky Way is one of its largest members, along with the Andromeda Galaxy, a magnificent spiral even bigger than our own, 2.5 million light years away. When you look at Andromeda, you're seeing it as it was when early hominids were first walking the plains of Africa. Andromeda and the Milky Way are on a collision course. In about 4.5 billion years, they'll begin to merge in a slow, cosmic dance. Their stars will mostly pass through each other like ghosts, but their gas clouds will collide, sparking a brilliant burst of new star formation. They'll eventually settle into a single, larger galaxy. But that's a story for another time. For now, we keep pulling back. The local group, with its 2 great spirals and dozens of smaller dwarf galaxies, now looks like a tiny, isolated cluster of lights. But it isn't isolated. As our view widens, we see that it's just one small part of a much, much grander structure. We're beginning to see the cosmic web. The universe isn't a random scattering of galaxies. Gravity has woven them into a vast, interconnected filamentary structure, like a celestial sponge. There are immense, galaxy-rich filaments, and massive nodes where these filaments meet, called superclusters. Separating them are truly enormous regions of near-total emptiness, known as voids. For a long time, we thought our local group was on the outskirts of the Virgo supercluster. But we now know that's just one piece of the puzzle. Both our local group and the Virgo supercluster are just arms of an even more colossal structure. A supercluster called Laniakea. In Hawaiian, it means immeasurable heaven. And the name fits. Laniakea is about 520 million light-years across and contains around 100,000 galaxies, all flowing towards a single point of immense gravity called the Great Attractor. Let that sink in. 100,000 galaxies, each home to billions, sometimes trillions, of stars. We live in one of them. Our full cosmic address is a planet, in a star system, in a galaxy, in the local group, which is part of the Laniakea supercluster. And Laniakea itself is just one of many. As we pull back even further, we see them stretching out in all directions. A web of light and structure, separated by the profound, dark nothingness of the great voids. We see colossal structures of galaxies stretching for billions of light-years, like the Sloan Great Wall. We're now viewing the universe on its largest scale. Or so it seems. A journey back in time. Something fundamental has been happening on our journey, something we need to face. As we've moved further from Earth, we've also been traveling deeper into the past. It's an unavoidable consequence of light having a speed limit. When we looked at Andromeda, we saw it as it was 2.5 million years ago. The galaxies in the Virgo cluster, 50 to 60 million years in the past. The most distant galaxies in Laniakea, hundreds of millions of years ago. Now, as we push billions of light-years from home, we're looking billions of years into the past. We're looking at a younger universe. And the galaxies out here look different. They're smaller, more chaotic, still getting their act together. They shine with the furious light of young, massive blue stars that live fast and die young. The light from these ancient galaxies has been traveling for so long, through a universe that has been expanding the whole time, that the light itself has been stretched. It's a phenomenon called cosmological redshift. Light that started out as blue or ultraviolet gets stretched into longer, redder wavelengths. The farther a galaxy is, the faster it's moving away from us, and the more its light is redshifted. This redshift is our main tool for measuring cosmic distances. We can now see galaxies as they were 10, 12, even 13 billion years ago. The light from these objects began its journey when the universe was just a baby. These are the infant galaxies, the first cities of stars. The James Webb Space Telescope is constantly pushing this boundary, finding surprisingly bright and structured galaxies just a few 100 million years after the Big Bang. Discoveries like these are challenging our models of how quickly the first stars and galaxies could have possibly formed. But our journey isn't over. We're pushing past these first galaxies, looking even deeper into space and further back in time. We're approaching a wall. Not a physical wall, but a wall of time. A point beyond which there are no more stars, no more galaxies to see. The wall of first light. We're now looking at light that has traveled for nearly 13.8 billion years to reach us. We are looking at the very dawn of time. And here, we find it. The edge of what we can see. But it's not darkness. It's a faint, pervasive, and almost perfectly uniform glow of microwave radiation, coming from every direction. This is the cosmic microwave background, or CMB. It is, quite literally, the oldest picture of the universe that exists. So what are we looking at? We're seeing a time just 380,000 years after the Big Bang. Before this moment, the universe was an impossibly hot, dense, opaque fog. A plasma of protons and electrons so hot that light particles, photons, couldn't go anywhere. They were instantly scattered and absorbed by free electrons, trapped in a cosmic game of pinball. The universe was dark, not because there was no light, but because the light was trapped. But as the universe expanded, it cooled. After 380,000 years, it hit a critical temperature about 3,000 Kelvin. At that point, it was finally cool enough for protons and electrons to combine and form the first stable hydrogen atoms. This event is called recombination. And just like that, the fog lifted. The photons were set free. The universe became transparent for the first time. The light that was present at that exact moment began to stream across the cosmos, and it's been traveling ever since. That light is what we see today as the cosmic microwave background. Of course, back then, it was a brilliant, fiery, yellowish-orange glow. But over the last 13.8 billion years, the universe's expansion has stretched its wavelength dramatically, redshifting it all the way from visible light down to the cool, low-energy microwaves we detect today. This CMB is the surface of last scattering. It's the boundary between the transparent universe we live in and the opaque plasma that came before. We can't see anything beyond it with a telescope, because light itself couldn't travel freely before then. This is the edge of our visible universe. It's a temporal horizon. It's our cosmos's baby picture. The particle horizon, an edge of information. So, is that it? Is the cosmic microwave background the edge of the universe? No. It's just the edge of what we can see with light. The universe almost certainly keeps going beyond it. This brings us to the real, scientifically defined, edge of our observable universe. The particle horizon. This idea can really bend your mind. The universe is about 13.8 billion years old. So you might think the farthest we could possibly see is 13.8 billion light years away. But that's not right. The actual radius of the observable universe is much, much larger. About 46.5 billion light years. How is that possible? The answer is the expansion of space itself. Imagine a single photon of light that left a distant galaxy right after the Big Bang, starting its long journey toward what would one day become Earth. As that photon traveled, the space between it and us was constantly stretching, like the surface of an inflating balloon. The photon is moving through space at the speed of light, but the space it has to cross is itself getting bigger. It's like trying to walk up a downward moving escalator. You're moving, but the goal is moving away from you at the same time. The region that emitted the light of the CMB we see today was much closer to us when it sent that light on its way. But in the 13.8 billion years since, the expansion of space has carried that region much farther away. Its actual distance from us now is about 46.5 billion light years. That distance defines the particle horizon. It's the boundary of the observable universe. A perfect sphere, with this at the very center, that encloses every particle whose information has had enough time to reach us since the beginning of time. This isn't a physical wall. It's an information horizon. It's a boundary defined by the speed of light and the age of the universe. There's absolutely no reason to think the universe just stops there. In fact, everything we can measure suggests it continues on, maybe forever. Beyond our horizon, there are almost certainly more galaxies, more superclusters, more everything. An observer in a galaxy 60 billion light years from us would have their own observable universe, their own particle horizon centered on them. Their bubble would include regions we can't see, and ours would include regions they can't. Every point in the cosmos is the center of its own observable universe. So what happens at the edge? At the particle horizon? The answer is simple and profound. Nothing. It's not a place you can go. It's a conceptual boundary that moves with you. If you traveled, new regions would come into view as their light finally reached you, while others would slip out of sight behind you. The edge isn't a destination. It's just the limit of our knowledge. The event horizon. An edge of no return. If the particle horizon wasn't strange enough, there's another, even stranger one. The cosmic event horizon. This one isn't about the past, but the future. It defines the boundary of what we will ever be able to see. For a long time, we thought the universe's expansion was slowing down, pulled back by gravity. If that were true, light from ever more distant galaxies would eventually reach us, and our view of the cosmos would slowly grow. But in the late 1990s, astronomers found something shocking. The expansion isn't slowing down. It's accelerating. A mysterious pressure in the fabric of spacetime, which we call dark energy, is pushing everything apart, faster and faster. This has a profound consequence. It creates a point of no return. There's a distance from us right now beyond which space is expanding so fast that it outruns the speed of light. Any galaxy beyond that point is being carried away from us faster than its light can travel toward us. Not because it's moving through space faster than light that's forbidden, but because the space between us and it is stretching so rapidly that the distance grows faster than light can cross it. This boundary is the cosmic event horizon, currently estimated to be about 16 or 17 billion light-years away. Notice that this is closer than the particle horizon. This means there are galaxies we can see right now whose ancient light is just reaching us today that are already beyond our cosmic event horizon. We are seeing their past, but their present is lost to us forever. The light they are emitting today will never, ever reach Earth. For decades, the story seemed to end there. As time goes on, more and more galaxies will cross this horizon and wink out, their light redshifted into oblivion. Our distant descendants would look up at an empty sky, with only our local group of galaxies for company, unaware that anything else ever existed. A lonely island in an endless void. But what if that's not the end of the story? Recent data has introduced a fascinating new wrinkle. Some evidence now suggests that dark energy might not be constant. It might be weakening. If it continues to weaken, gravity could one day take over again, reversing the expansion and pulling everything back together in a big crunch. It's a dramatic twist, suggesting our universe might not be headed for a cold, empty future, but a hot, dense one. The trillions of years of lonely expansion is no longer a certainty. The truth is, we are on the edge of a great mystery, and the final fate of the universe is once again an open question. The great unknown. What lies beyond? We've journeyed from home, past stars and galaxies, to the wall of first light. We've understood the horizons that limit our view of the past and our connection to the future. We've seen that the edge of the universe isn't a place, but a series of nested, observer-dependent boundaries. So we're left with the ultimate question. What is the nature of the entire universe, beyond what we can observe? Is it finite or infinite? The honest answer is, we don't know. But we have clues. Our best measurements of the CMB suggest that, on the largest scales, the observable universe is almost perfectly flat. According to Einstein's theories, a flat universe is most simply an infinite one. If you traveled in a straight line, you'd travel forever. It would have no edge and no center. Just more galaxies, more clusters, more voids, forever. But there is another possibility. The universe could be finite, but unbounded, like the surface of a sphere. An ant on a ball can walk forever without falling off an edge, and eventually end up back where it started. The universe could be a three-dimensional version of that, a hypersphere. It would be finite, but so unimaginably vast that it would seem flat and infinite to us, like sailors on a giant planetary ocean who can only see a flat horizon. And then you get to the truly wild ideas. The multiverse, which suggests our entire universe is just one bubble in a cosmic foam of other universes, each potentially with its own laws of physics. This is deep speculation, where science and philosophy meet. Our journey has taken us across scales that defy intuition, from the familiar ground under our feet to the theoretical shores of infinity. We've seen that the question, what's at the edge of the universe, doesn't have a simple answer, because the edge itself is a beautiful and complex idea. It's a horizon of light, of time, and of knowledge. The curiosity that drives us to ask these questions is one of the best things about being human. The universe doesn't give up its secrets easily, but the quest itself is an incredible journey. If you feel a sense of awe at the vast, silent beauty of it all, you are not alone. If this journey sparked your curiosity, consider subscribing and joining our community of cosmic travelers. We'll keep exploring the biggest questions in the cosmos, from the darkness of black holes to the dawn of life. We'd love to hear your thoughts. What part of this journey was the most mind-bending for you? Let us know in the comments. A calm journey to nothingness. We end where we began, in thought, floating in the quiet space between galaxies. We've traveled to the supposed edge of everything, only to find it's not an edge at all. It's a horizon. An elegant boundary defined not by matter, but by light and time. The edge of the universe isn't a place of violent collision or a sudden drop-off. It's a place of quiet recession. The gentle fading of light from galaxies carried away on the tide of expanding space. The nothingness of our journey isn't an empty void that the universe is expanding into. The nothingness is the nothingness of information. The eternal silence from realms beyond our cosmic horizon. There's a certain peace in this. Our universe isn't a small, confined room. It's either an infinite expanse or a realm so vast it might as well be. We aren't staring at a wall. We're looking out from a tiny island across a limitless ocean, and the horizon we see is simply the limit of our own vision. The most beautiful thing is that this horizon of knowledge is not static. As science progresses, as our telescopes get better, our horizon expands. We push back the darkness, even if just a little. We see a little farther, understand a little deeper. So, the next time you look up at the night sky, remember this journey. Remember the silent dance of planets and stars, the sprawling cities of galaxies, the ancient light from the dawn of time, and the horizons that define our cosmic view. You aren't just looking at points of light. You're looking at distance, at time, and at the profound, humbling, and beautifully calm mystery of what it means to exist in this immeasurable heaven. The journey doesn't end. The journey is endless. Fall asleep drifting to the edge of our solar system. Close your eyes. And just let go. We're beginning a peaceful voyage tonight. A slow drift from our familiar blue planet out to the mysterious edges of our solar system. There's nothing you need to do. And nowhere you need to be. Just allow my voice to be your guide. As your body sinks deeper and deeper into the surface beneath you. Feel that gentle pull of gravity. A comforting weight. Because soon, we're going to leave it all behind. We will travel across unimaginable distances, discovering our true place in the cosmos. As you gently, peacefully, drift off to sleep, let each word wash over you, like a soft cloud passing in a calm, night sky. Your breathing is slow and steady, in and out. Each breath takes you further away from the day, further from your worries, and closer to a state of profound peace. The journey has already begun. If you enjoy this journey tonight, and find some peace in this voyage through the stars, please consider liking this video or subscribing. It helps our quiet corner of the cosmos reach others who might also be looking for a gentle escape, a peaceful drift into sleep. Thank you. Now, let's continue our journey. Let everything else just fade away. Leaving Earth. Focus on your breath. A gentle rhythm. like the soft, silent turning of the earth itself. Imagine yourself now, perfectly still and comfortable. And you're beginning to float. A gentle lift. Completely effortless. As if you're a feather caught in the quietest of updrafts. You are rising. Slowly. Peacefully. Up above your room. Above your town. Ascending into the deep, velvet dark of the night sky. The sounds of the world start to fade. That distant hum of traffic. The whisper of wind in the trees. It all recedes, replaced by a deep and comforting silence. You are so safe. You are so secure. Looking down, you can see the world as a patchwork of sleeping towns and dark countrysides, speckled with tiny jewels of light. The cities glow like embers in the vast darkness. You keep rising. Higher and higher. The air grows thin, but you can breathe perfectly. You don't need anything. You are simply an observer. The curve of the earth becomes clear. A gentle, sweeping arc against the infinite backdrop of space. It's a sight that inspires awe. But tonight, it only inspires calm. That is home. And you are peacefully drifting away from it. Now, you can see the whole of our planet. A beautiful, swirling marble of blue, white, and green. Suspended in the quiet emptiness. This is the pale blue dot. A thought to hold as we drift. A reminder of the tranquil beauty we've come from. And right beside it, a smaller, silent companion. The moon. Our first destination is this familiar celestial body. The journey is short, just a gentle hop in cosmic terms. It's about 384,000 kilometers away. A number so large it feels meaningless to the sleeping mind. So instead, just think of it as a quiet float. A slow, patient drift. Astronauts have made this trip, leaving footprints in the gray dust that are still there today, completely undisturbed. As we approach, the moon grows in your mind's eye. It's not the flat, silver coin we see in the night sky, but a sphere of craters and mountains. Of silent, ancient plains. Its surface is a history book of cosmic impacts. Every crater a memory of a time long, long past. There is no air here. No wind, no sound. The silence is absolute. It is a silence that deepens your own sense of peace. A silence that absorbs all thought. And all worry. We don't land. We are merely observers. Drifting past. You see the earth from here. A vibrant blue and white jewel hanging in the blackness. It looks so fragile. And so incredibly beautiful. All the concerns of that world seem so small. So distant. Let them fade. Let them dissolve into the vastness. Your body is light. Completely weightless. Your mind is even lighter. Free from the day. Free from everything. You are drifting. Peacefully. Onward. Journey towards the sun. Our voyage continues. We leave the earth and moon behind us. Two tiny spheres shrinking in the rear view of our consciousness. Our vessel is your imagination. Fueled by your desire for rest. It moves without a sound. Without any effort. We are turning now. Turning toward the heart of our solar system. The sun. From here, it is a brilliant, distant star. The brightest light in the sky, but it's not yet overwhelming. We won't travel to its fiery surface, of course, but we'll drift toward its domain, to feel its presence from a safe and comfortable distance. The distance to the sun is about 150 million kilometers. This immense gap is what scientists call one astronomical unit. It's the yardstick of our solar system. If the trip to the moon was a single step, this journey is like a long, unhurried walk of nearly 400 steps. But we don't need to walk. We just float, drifting on the quiet currents of space. As we travel, the sun grows from a point of light into a small, brilliant disk. Its light is pure, unwavering. It's the light that warms our world, the light that fuels all life. That light takes 8 minutes to travel from the sun to the earth. It travels with incredible speed, yet we are moving with incredible slowness. There is no rush. The slower we go, the deeper you drift. Let the idea of the sun's light warm you. Feel a gentle, comforting warmth spread through your body. Not hot, just a pleasant, soothing glow. Like resting in a patch of sunlight on a cool afternoon. Let this warmth relax every single muscle. From the tips of your toes, all the way to the top of your head. As we drift, we pass the orbits of the inner planets. First, Mercury, the closest to the sun. A small, cratered world, baked by the sun's constant energy. It moves so quickly in its orbit, a little world in a hurry. But we're not in a hurry. We drift past its path, acknowledging its place in this cosmic dance, and just continue on. Then, there's Venus, shrouded in thick, yellowish clouds. A world of intense pressure and heat. Its secrets are hidden beneath that impenetrable atmosphere. We float past its orbit, untroubled by its harshness, remaining in our own perfect bubble of tranquility. Our journey is one of peace. We observe these worlds from a distance, the way you might observe shells on a beach. Each one is unique, each with its own story, but none of them require anything from us. We are simply passing through. The sun now appears larger. A perfect circle of light. Its warmth is a constant, gentle presence. Sunlight is usually a cue for our bodies to be awake and alert. But here, on our journey, we are using its idea not to wake, but to deepen our relaxation. We are bathed in the asterisk concept of light. A pure, cleansing, silent light that washes away the darkness of a busy mind. Imagine this light filling your awareness. A clean, white, peaceful light. It holds no heat, no intensity. Only peace. You are drifting in this light, floating in a sea of calm. Your thoughts are quiet. Your body is still. The hum of the universe is a gentle lullaby. And you are sinking into a profound state of rest. Mars and the asteroid belt. We continue our drift outward now, leaving the sun and its closest companions behind. We are moving away from the warmth, out into the cooler, deeper parts of the solar system. The sun shrinks once more, back to a brilliant, powerful star. Our home, Earth, is now just a faint, bluish point of light, almost lost in the glare. Our next point of interest is Mars, the red planet. As we approach its orbit, we see it hanging in the darkness. A world of rusty red dust and pale pink skies. It's a smaller world than Earth, and a colder one. A world of silent deserts and towering, extinct volcanoes. It has 2 tiny, misshapen moons, Phobos and Deimos. Their names mean fear and panic, but we feel neither. We are in a state of perfect calm. We drift past this sleeping, red world, a silent observer in the night. Mars is a world of quiet wonder. It has canyons that dwarf any on Earth, and polar ice caps that grow and shrink with the seasons. It holds the memory of water, of ancient rivers and lakes that have long since vanished. It is a world of beautiful desolation. A quiet, dusty jewel in the darkness. We watch it for a little while. Its soft, reddish glow a soothing sight. And then we let it go. We drift onward. Beyond the orbit of Mars lies a vast, open space. It's a boundary between the inner, rocky worlds and the outer giants we have yet to see. This is the realm of the asteroid belt. You might imagine the asteroid belt as a dense, chaotic field of tumbling rocks. Impossible to navigate. But the reality is much calmer. Much emptier. The asteroid belt is a region of immense emptiness, sparsely populated by rocks and dust. The asteroids are, on average, millions of kilometers apart. There is no danger here. No chaos at all. We are drifting through a silent, empty space, dotted with ancient, lonely rocks. These are the leftovers from the formation of the solar system. Building blocks of planets that were never meant to be. Their creation stopped by the immense gravity of a giant we have yet to meet. Imagine these asteroids. Some are small, like pebbles. Others are enormous, hundreds of kilometers across, large enough to be considered minor planets. They all tumble slowly through space, on long, lazy orbits around the Sun. They've been here for billions of years. Silent witnesses to the history of our solar system. There is a deep sense of peace in this emptiness, a sense of timelessness. The worries and pressures of your life, they're tied to a sense of urgency, of time. Here, in the asteroid belt, time stretches into near infinity. 1,000 years is just a moment. Let that sense of infinite time wash over you. There is nothing to do, nothing to rush for. You have all the time in the universe. Your breathing is slow and deep. Your body is heavy and relaxed. Your mind is quiet and still. We are drifting, floating through this ancient, silent garden of stones. Each one is a world in itself, with its own history, its own silent story. We aren't disturbed by them. We are calmed by their presence, by their silent, patient existence. We continue our journey outward, leaving the asteroid belt behind. The space ahead is even darker, even more vast. We're heading into the realm of the giants. And as we drift, you sink deeper and deeper into sleep. The gas giants, Jupiter. The nature of our journey now changes. We've left the small, rocky worlds of the inner solar system far behind us. We are crossing a great divide into the kingdom of the gas giants. The Sun is now a distant, but still powerful, star. Its light is weaker here, the surrounding darkness more profound. And in that darkness, a new light begins to grow. Not the sharp, brilliant light of a star, but the soft, reflected glow of a colossal planet. This is Jupiter, the king. It is so immense that it's more massive than all the other planets in our solar system combined. It is a world on a scale that is difficult for the mind to even hold. If it had grown just a little larger, it might have become a star itself. As we drift closer, its size becomes truly apparent. It fills our view. A majestic, swirling globe of colored bands. Stripes of cream, ochre, and brown circle the planet. These are clouds of ammonia and water, stretched into vast jet streams by the planet's incredibly fast rotation. A day on Jupiter lasts only 10 hours. This rapid spin creates weather on a staggering scale. And the most famous feature of this weather is the Great Red Spot. We drift towards this feature. A storm. A hurricane. So large that it could swallow the entire Earth with room to spare. It's a swirling vortex of crimson clouds that has been raging for centuries. A testament to the power contained within this giant world. Watching it from our safe, peaceful distance. It isn't terrifying. It's hypnotic. A slow, majestic dance of unimaginable forces. The colors swirl and blend. A cosmic masterpiece painted by physics. Jupiter doesn't have a solid surface you could stand on. It's a giant ball of gas and liquid. Mostly hydrogen and helium. If we were to descend into its atmosphere, the pressure would grow and grow until the gas around us became a strange, exotic liquid. Deeper still, scientists believe there may be a core. Perhaps a solid kernel. Or maybe a strange, super-hot soup of materials under immense pressure. Its secrets are buried deep within its cloudy heart. But we are content to stay on the outside, drifting peacefully in its orbit. And Jupiter is not alone. It is its own little solar system. A gravitational monarch attended by a court of dozens of moons. As of early 2026, we know of at least 95 confirmed moons, and likely many more waiting to be found. We see the four largest, the Galilean moons, discovered by Galileo centuries ago. They look like tiny pearls circling the immense planet. There is Io, the volcanic moon. A world constantly torn and reshaped by Jupiter's gravity, its surface covered in active volcanoes that spew sulfur into space, painting it in shades of yellow, red, and black. There is Europa, the ice moon. Its surface is a fractured shell of water ice, crisscrossed with long, dark lines. Beneath this icy crust, scientists believe there is a vast, hidden ocean of liquid water. Perhaps one of the most likely places to find life beyond Earth. There is Ganymede, the largest moon in the entire solar system. Even larger than the planet Mercury. It's a world of rock and ice, and it is the only moon we know of that has its own magnetic field, creating faint auroras at its poles. And there is Callisto, the ancient moon. Its surface is dark and heavily cratered. One of the oldest and most unchanged surfaces in our solar system. A quiet, frozen record of cosmic history. We drift among these worlds. A silent, ethereal ballet. Jupiter hangs in the background, a majestic, painted sphere. Its moons orbit in a slow, graceful rhythm, a cosmic dance that has been going on for billions of years. The sheer scale of this system is humbling. It makes our own worries and concerns feel incredibly small. Insignificant. Let that feeling wash over you. Let your problems shrink and fade away. In the face of this cosmic grandeur, your mind is calm. Your body is deeply relaxed. You are drifting peacefully in the shadow of a giant, on the verge of a deep and restful sleep. The ringed planet, Saturn. We gently pull away from the grand system of Jupiter, its swirling storms and dancing moons fading into the distance. Our journey continues outward, into the ever deeper quiet of the outer solar system. The darkness ahead is punctuated by a new point of light. It's a soft, yellowish glow. As we drift closer, it resolves into one of the most beautiful and iconic sights in all of creation. Saturn, the jewel of the solar system. Like Jupiter, Saturn is a gas giant, composed mostly of hydrogen and helium. It's a huge world, but it's the least dense planet in our solar system. It is so light for its size that if you could find a bathtub large enough, Saturn would float. Its atmosphere is a pale, butterscotch yellow, due to ammonia crystals in its upper layers. The winds here are among the fastest in the solar system, reaching incredible speeds. But from our vantage point, the planet appears serene, calm, majestic. And then, there are the rings. From a distance, they look like solid, luminous structures, a shimmering halo around the planet. But as we drift closer, we see them for what they truly are. Saturn's rings are not solid. They are made of billions upon billions of individual particles of ice and rock. These particles range in size from tiny grains of dust to chunks as large as a house, or even a mountain. They're the remnants of comets, asteroids, or shattered moons, torn apart by Saturn's immense gravity and spread out into a vast, flat disk. We are now drifting alongside these rings. The sight is breathtakingly beautiful and deeply peaceful. Imagine an immense, silent river of ice flowing around the planet in perfect orbital harmony. The sunlight from the distant sun catches the ice particles, making them glitter and shine like a field of scattered diamonds. The rings are incredibly wide, stretching for thousands upon thousands of kilometers. Yet they are astonishingly thin. In most places, they are only about 20 meters thick, a cosmic sheet of paper. We can see the gaps in the rings. Dark, empty lanes carved out by the gravity of Saturn's many moons. The largest of these gaps is the Cassini division, a huge space that separates the main rings. Each ring, and each particle within it, orbits Saturn at its own specific speed. The inner rings move faster than the outer ones. It is a silent, cosmic symphony of motion. A perfectly ordered and graceful dance. There is no sound here. Just the slow, steady turning of the planet and the silent, shimmering river of its rings. We float above this incredible spectacle. Below us, the golden globe of Saturn. Around us, the glittering, ethereal rings. It is a place of profound beauty and order. It calms the mind and soothes the soul. Let the image of Saturn and its rings fill your awareness. Let its perfect, ordered beauty bring a sense of order to your own mind. Let go of any chaotic or troubling thoughts. Let them be smoothed out, like the perfect, circular orbits of the rings. Saturn, too, has a large family of moons. In fact, with recent discoveries confirmed in 2025, it is the new Moon King of our solar system, with an incredible 274 known moons. We see its largest moon, Titan, a world larger than Mercury. Titan is unique, as it's the only moon in the solar system with a thick, substantial atmosphere. It's a hazy, orange world, with rivers, lakes, and seas of liquid methane and ethane on its surface. Another moon, Enceladus, is a small, bright, icy world. It continuously spews jets of water vapor and ice particles from its southern pole, feeding one of Saturn's faint outer rings. It is a world with a hidden, subsurface ocean, another potential haven for life. The entire Saturnian system is a marvel of quiet, majestic beauty, a place of deep peace. Allow this peace to settle over you. A soft blanket of calm. You are drifting, floating, letting go. The rings of Saturn are a perfect, endless loop. A mantra for the sleepy mind. Round and round. Deeper and deeper. Into a state of complete and total relaxation. The ice giants, Uranus and Neptune. Our voyage carries us onward, away from the golden light of Saturn and its shimmering rings. We are now venturing into the deep, dark frontier of the solar system. From here, the sun is just a very bright star. Its warmth is gone, replaced by a profound, interstellar cold. The darkness is almost absolute. But in this deep darkness, two faint, ghostly lights appear. They are the ice giants, Uranus and Neptune. These two worlds are similar in size and composition, smaller than Jupiter and Saturn, but still immense compared to Earth. They're called ice giants because they're made up mostly of a hot, dense fluid of icy materials, water, methane, and ammonia, all surrounding a small, rocky core. First, we approach Uranus. It is a strange and mysterious world. From a distance, it appears as a pale, featureless orb of cyan or pale blue-green. This color comes from the methane gas in its atmosphere, which absorbs red light and reflects blue and green. Uranus is the coldest planet in the solar system, with temperatures in its atmosphere dropping to an incredible -224 degrees Celsius. This is because, unlike the other giant planets, Uranus radiates almost no internal heat. It is a cold, quiet world. But the strangest thing about Uranus is its tilt. It's tilted on its side by an incredible 98 degrees. It orbits the sun like a rolling ball, spinning sideways. Scientists believe this extreme tilt may be the result of a cataclysmic collision with an Earth-sized object, long ago in the solar system's history. Because of this tilt, its seasons are extreme. Each pole gets 42 years of continuous sunlight, followed by 42 years of complete darkness. We are drifting past this sideways world. A quiet, sleeping giant in the cold darkness. Like the other giants, Uranus has rings, though they are faint and dark, made of material as black as charcoal. And it has a family of 28 small moons, named after characters from the works of William Shakespeare and Alexander Pope. We leave this strange, tilted world behind and continue our drift outward. Ahead of us lies the last of the planets, Neptune. It's a world of deep, vibrant, azure blue, much more vivid than the pale cyan of Uranus. It, too, gets its color from methane gas, but its deeper blue suggests something else is at work in its atmosphere. While Uranus appeared calm and sleepy, Neptune is a dynamic and stormy world. It has massive dark spots that are hurricane-like storms, similar to Jupiter's Great Red Spot, though they are much more short-lived. The winds on Neptune are the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour. From our safe distance, we see these storms as faint, dark smudges on the planet's beautiful blue face. We see the wispy, white clouds of frozen methane that streak across its upper atmosphere. Neptune is incredibly far from the Sun, about 30 times farther than Earth. The sunlight that reaches it is 900 times fainter than the sunlight we experience. It is a world of permanent twilight. And yet, Neptune radiates more than twice the energy it receives from the Sun. It has a powerful internal heat source, left over from its formation billions of years ago. This inner furnace is what drives its dynamic weather. Deep inside both Uranus and Neptune, the pressures and temperatures are so extreme that scientists believe it might rain diamonds. Carbon atoms, squeezed from methane, could crystallize and fall through the dense, fluid mantle like hailstones. An unimaginable, beautiful process hidden deep within these blue worlds. We're at the edge of the planetary system now. Neptune is the last outpost. Beyond it lies a new and even more mysterious realm. As we drift past this final, beautiful blue world, let the sense of distance and cold deepen your relaxation. The cares of your world are so far away now, they are almost forgotten. You are floating in the deep, silent, cold of space. And it isn't frightening. It is peaceful. It is the peace of immense distance. The peace of profound quiet. Your body is completely at rest. Your mind is clear. You are on the very edge of sleep. The Kuiper Belt. We have now passed the orbit of Neptune, the last of the great planets. Our journey has taken us to the frontier of the known solar system. The Sun is now just a star. Brighter than any other, but still just a point of brilliant light in the endless black. We are entering a new region. A vast, donut-shaped ring of icy bodies known as the Kuiper Belt. This is the third zone of the solar system, a vast, frozen wilderness. It begins at Neptune's orbit and stretches out into the darkness for billions of kilometers. Like the asteroid belt, it is a region of leftovers from the solar system's formation. But where the asteroid belt was mostly rock, the Kuiper Belt is mostly ice. The objects here are made of frozen water, ammonia, and methane. This region is far, far larger and more massive than the asteroid belt. It's thought to contain hundreds of thousands of icy bodies larger than 100 kilometers across, and perhaps trillions of smaller comets. Yet, just like the asteroid belt, the Kuiper Belt is a place of unimaginable emptiness. The space between these objects is vast. We are in no danger as we drift through. We are floating into a realm of deep cold and perpetual twilight. The temperatures here are just a few tens of degrees above absolute zero. And in this frozen expanse, we find Pluto. For decades, we knew it as the ninth planet. Now, we understand it as the king of the Kuiper Belt. A large, complex, and fascinating dwarf planet. As we drift by, we see its surprisingly varied surface. There are mountains made of solid water ice, vast plains of frozen nitrogen, and a thin, hazy atmosphere. It even has a large, heart-shaped glacier on its surface. It's a dynamic and geologically active world, even out here in this extreme cold. Pluto is not alone. It has 5 moons of its own. The largest, Charon, is so big that the two worlds are often considered a binary system, orbiting a common point in space. We drift past other large objects in this belt. Worlds like Eris, Makemake, and Haumea. Each one a distant, icy kingdom. We pass Arrokoth, a strange, snowman-shaped object that was visited by the New Horizons spacecraft. It is 2 bodies that gently fused together, a pristine relic from the very beginning of the solar system. These Kuiper Belt objects are the source of many of the comets we see. Every now and then, the gravitational pull of Neptune will nudge one of these icy bodies out of its orbit, sending it on a long journey towards the inner solar system. There is a deep sense of antiquity here. We are drifting through the most primitive material in our solar system. A cosmic deep freeze that has preserved the building blocks of the planets for 4.5 billion years. The silence is profound. The darkness is complete, save for the distant light of the stars and the incredibly faint light of the far-off sun. Let this deep, ancient silence envelop you. Let the profound cold relax you. There are no demands here, no expectations. Just the slow, patient drift through this frozen, silent realm. Your thoughts slow down, becoming as slow and patient as the long orbits of these icy worlds. Your body is heavy, still, and deeply relaxed. You are letting go completely, drifting. On the very edge of our solar system. And on the very edge of a deep, restorative sleep. The heliopause and Voyager. our journey is reaching its final, most mysterious stages. We have left the Kuiper belt behind. The Sun is now just one star among many, although it's still the brightest. We are drifting through a region that no human has ever seen with their own eyes. A place defined not by what is there, but by what isn't. We are approaching the boundary of the Sun's influence. The Sun emits a constant stream of charged particles called the solar wind. This solar wind travels outward in all directions, creating a vast, protective bubble around our solar system. This bubble is called the heliosphere. It shields the planets from the harsh radiation of interstellar space. For our entire journey so far, we have been inside this bubble. Now, we are approaching its edge, the place where the solar wind finally slows down and pushes against the wind from other stars. This boundary is called the heliopause. This is the true edge of our solar system, the border between the Sun's kingdom and the vast, open ocean of the Milky Way galaxy. As we drift through this region, we are not alone. There are two tiny, silent emissaries from our world that have traveled here before us. The Voyager 1 and Voyager 2 spacecraft. Launched way back in 1977, these small, robotic explorers have been traveling for decades. They are the most distant human-made objects in existence. Imagine one of them now, drifting silently in the darkness. A small, golden machine, covered in antennas and instruments. It is still sending faint signals back to Earth, a journey that takes more than 22 hours for the light-speed radio waves to complete. Voyager 1 crossed the heliopause and entered interstellar space in August of 2012. It is the first object from humanity to ever do so. It is now sailing on the cosmic seas between the stars. It carries with it a golden record. A phonograph record containing sounds and images of Earth. A message in a bottle cast into the cosmic ocean, intended for any civilization that might one day find it. It's a symbol of our curiosity, our hope, our desire to reach out into the vast unknown. To be in this place is to feel a sense of profound solitude, but also connection. Connection to these brave, lonely little probes, and to the people who sent them on their way. The space here isn't entirely empty. It's filled with a thin, tenuous plasma. A mix of particles from our Sun and particles from distant, long-dead stars. The silence is absolute. The darkness is complete. The sense of scale is overwhelming and deeply calming. You are now further from your home than any human has ever been. And you are perfectly safe, perfectly at peace. Your worries, your anxieties, they belong to a tiny blue dot, billions and billions of kilometers away. They can't reach you here. Let them go. Feel the vastness. Feel the silence. Feel the peace. You are on the threshold of interstellar space, and the threshold of deep, deep sleep. Allow yourself to cross over, let go of the journey, and just drift. The Oort cloud. We've crossed the heliopause. We are now in interstellar space. The Sun's solar wind is behind us. We are in the space between the stars. But our solar system has one last, vast, and mysterious component to reveal. We are entering the realm of the Oort cloud. This isn't a belt, like the asteroid or Kuiper belts. It is a giant, spherical shell of icy objects that surrounds our entire solar system. A thick, hollow bubble of comets, enclosing everything we have journeyed past. It is the most distant region of our solar system, and its scale is almost impossible to imagine. Its inner edge is thought to begin somewhere between 2,000 to 5,000 astronomical units from the Sun. Remember, 1 astronomical unit is the distance from the Earth to the Sun. The Voyager 1 spacecraft, traveling at 1 million miles a day, will not reach the inner edge of the Oort cloud for another 300 years. And the cloud extends outward from there, perhaps to 50,000, or even 100,000. It may reach almost halfway to the nearest star. No one has ever seen the Oort cloud directly. It is too far, too dark, too faint. Its existence is a theory proposed by the astronomer Jan Oort in 1950 to explain where long-period comets come from. These are comets with orbits that last for thousands, or even millions, of years. The Oort cloud is thought to contain billions, or perhaps even trillions, of these icy bodies. Most are composed of frozen water, methane, ethane, and other ices. These are the most ancient and pristine objects in our solar system. Leftovers from its very birth, flung out to these incredible distances by the gravity of the giant planets long ago. They are only loosely bound by the Sun's gravity. They drift in slow, lazy orbits, like moths around a distant porch light. Their orbits aren't confined to the flat plane of the planets. They come from all directions, forming a vast, spherical halo. Occasionally, the gravitational nudge of a passing star, or the tide of the Milky Way galaxy itself, will disturb one of these icy worlds and send it on its long fall towards the Sun. We are drifting through this theoretical, ghostly realm. Imagine a space so vast and so empty that it is almost pure nothingness. And scattered throughout this nothingness, trillions of silent, frozen comets. They are separated by immense distances, millions of kilometers apart. The Sun from here is just a star. A very bright star, but one among countless others in the glittering tapestry of the Milky Way. Its light is faint. Its warmth is non-existent. We are in the deep, cold, silent darkness of the cosmos. There is nothing to see here, nothing to do, nothing to think. There is only the sense of immense, peaceful, and eternal space. This is the final frontier of our solar system, the cosmographic boundary between our home and the rest of the universe. And it is the perfect place to let go. Let go of the journey. Let go of my voice. Let go of all thought. Become one with the emptiness. Become one with the silence. Become one with the peace. You have drifted to the very edge of the solar system. And now, you can drift into the infinite, peaceful expanse of your own deep sleep. The journey continues. But your awareness can now fade. You are floating in the Oort cloud, a place of perfect peace and stillness. The faint light of the distant Sun is a single, peaceful star. The trillions of sleeping comets are your silent companions. There is no time here, no pressure, no worry. Only a deep, profound, and endless calm. Allow this calm to be the last thing you feel. Allow the darkness to be a soft, comforting blanket. Allow the silence to be the sound of your own peaceful rest. The universe will watch over you. You live inside 400 billion stars. You are here, right now, on a tiny, fragile world, spinning around a single star at over 66,000 miles per hour. But this star, our Sun, is also a traveler. It's moving at an astonishing 515,000 miles per hour, racing around something so massive, so powerful, that it holds not one, not a million, but hundreds of billions of other stars in its grip. Your star is just one of up to 400 billion, a single speck of light in a city of stars so huge it takes light 100,000 years just to cross it. This is your home. This is the Milky Way. And tonight, we're going to take a slow journey through the city you live in, to really feel the unbelievable scale of your place in the universe. This isn't a story about distant, alien things. This is the story of your address, your neighborhood, your city, written on the biggest scale imaginable. The address. To understand the city, you first have to know your own street, your home. We'll start on Earth, a sphere of rock and water, an oasis of life in what looks like an endless, empty void. From our perspective, it feels like everything. But in the language of the cosmos, distance isn't measured in miles or kilometers. It's measured by the speed of light. Light zips along at 186,000 miles every single second. It's the universe's ultimate speed limit. That familiar distance to our own moon, about 250,000 miles, is crossed by light in just over a second. Think about that. The entire history of humanity has played out beneath a companion that is, cosmically, just 1 second away. Now, let's look at the heart of our own little system. The sun. The light that warms your face on a summer day started its trip 8 minutes before it reached you. The sun is 8 light minutes away. This one star holds 99.8% of all the stuff in our solar system. It's our anchor, our furnace, and the gravitational center of our family of planets. We are all, from the gas giants to the smallest asteroid, completely tied to its power. But our solar system is much bigger than we usually think. Let's travel further, past Mars, past the great asteroid belt, past the giants Jupiter and Saturn, and beyond the icy worlds of Uranus and Neptune. Out here, at the edge of the planets, we find messengers we sent out a lifetime ago. The Voyager probes, launched back in the 1970s, have now been traveling for half a century. As of 2026, they are just crossing into the space between stars, a journey that has taken them over 23 light hours to complete. They're the farthest things humans have ever sent from home, whispering data back to us across a gap so wide their messages, even moving at light speed, take nearly a full day to get here. And yet, this still isn't the true edge of our address. Our star's influence reaches much, much further. We're just getting started. We're still standing on our own front porch, looking out at the street. The city is waiting. Leaving the neighborhood. To really leave home, we have to travel to the farthest edge of the sun's kingdom, the Oort cloud. We've never actually seen it, but we think it's there because of the comets that occasionally fall into the inner solar system. It isn't a ring or a belt, but a giant, spherical shell of trillions of icy objects, surrounding our solar system like a ghostly bubble. This sphere is huge, possibly stretching out for a light year, maybe even 2, in every direction. From here, the sun would just be an unusually bright star, its warmth gone, its gravitational pull incredibly weak, but still there. Here, a full light year from home, we've finally reached the edge of our solar system. We've traveled for an entire year at the fastest speed possible, just to leave our own star's territory. Now, for the first time, we can look out into true interstellar space. The void between the stars. And it is profoundly empty. Our closest stellar neighbor is Proxima Centauri, and it's over 4 light years away. Let's put that into perspective. If our sun were a grapefruit in New York City, Proxima Centauri would be another grapefruit in San Francisco. And between them? Almost nothing. A few scattered atoms of gas and dust. This is the space between the houses in our galactic city, a vast, dark, and lonely expanse. To travel from our Sun to Proxima Centauri, even at the incredible speed of the Voyager probes, would take over 75,000 years. The stars that look so close in our night sky are really islands of light, separated by oceans of darkness so wide our minds can barely comprehend it. This is what our galactic neighborhood is like. It's not a crowded suburb. It's more like a few distant farmhouses, each with a huge property, separated by unimaginable distances. And the journey we've taken so far, across 1 light-year of space, is just a single step. Our galaxy, the city we live in, is 100,000 light-years across. We've taken one step on a journey that would need 100,000 more just like it. Now, it's time to head into the city itself. The city limits. As we pull back, the scale begins to change. Individual stars, which were our main landmarks, start to blend into a much larger structure. We start to see the city's architecture. We are inside one of its great residential districts, a spiral arm. Our specific address is the Orion Cygnus arm, or more simply, the Orion arm. It's easy to picture this as some grand, busy boulevard of stars, but it's actually more subtle. The Orion arm is considered a minor arm of the Milky Way. Think of it as a quieter, residential side street. It's about 500 light-years wide and estimated to be around 20,000 light-years long. Our solar system is nestled right on its inner edge. The beautiful constellations we see from Earth, like the great hunter Orion that our arm is named after, are made of brilliant, massive stars that are our relatively close neighbors in this very arm. Betelgeuse, Rigel, the stars of Orion's belt, these are the local landmarks on our street. They look like a connect-the-dots pattern from our backyard, but they're really massive, powerful stars scattered across thousands of light-years inside our shared spiral arm. So what even is a spiral arm? It's not a solid thing that rotates like a pinwheel. If it were, the inner parts would spin faster than the outer parts, and the whole spiral shape would wind itself up and disappear. Instead, a spiral arm is what scientists call a density wave. Think of it like a traffic jam on a highway. The jam itself, the area where cars are slowed down, can stay in one spot for hours, even as individual cars are constantly moving through it. A spiral arm is a cosmic traffic jam. It's a region of higher density, a wave of compression moving through the galaxy's disk. As this wave plows through clouds of gas and dust, it squeezes them, setting off furious bursts of star formation. This is why spiral arms are so bright. They're filled with brilliant, young, hot, blue stars that are born inside them. These young stars live out their short, dramatic lives inside the arm where they were born. But other stars, like our Sun, are just passing through. Our solar system isn't permanently stuck in the Orion arm. We drift in and out of these density waves over millions of years. For now, we happen to be cruising through this quieter part of the galaxy. That might seem like a minor detail of our location. But as we're about to see, living on this specific side street, and not on one of the galactic superhighways, may be one of the most important reasons we're here to wonder about it at all. The galactic habitable zone. Our position in the galaxy can feel totally random, just a tiny speck in a structure so big it's hard to fathom. But a growing body of evidence suggests our location might be anything but. It seems to be special, almost impossibly fortunate. We appear to live in what some scientists call the galactic habitable zone. To understand why our neighborhood is so special, we have to look at the more dangerous parts of town. The Milky Way has two major, dominant spiral arms that are far larger and more chaotic than our little Orion arm. The Perseus arm and the Scutum Centaurus arm. Our Orion spur is tucked right between these two galactic titans. If our arm is a quiet side street, the Perseus and Scutum Centaurus arms are 8-lane superhighways at rush hour. They are regions of immense activity and immense danger. The density of stars and gas is much higher. Star formation is happening everywhere, which sounds beautiful, but it means those arms are flooded with intense radiation from massive young stars. Supernovae, the cataclysmic explosions of dying giant stars, are far more common. These explosions can sterilize huge regions of space, blasting any nearby planets with deadly gamma rays. On top of that, the gravitational chaos in these arms is intense. The crowded stars pull on each other, disrupting planetary orbits, potentially flinging planets into their suns or ejecting them into the cold, empty darkness. While the idea is still debated, some scientific models suggest that a vast majority of stars in our galaxy may be unable to support life because they spend too much time passing through these deadly spiral arms. And this might just be our cosmic lottery ticket. Our solar system doesn't seem to plunge through these dangerous arms. We're in a uniquely quiet spot between them. Better yet, our orbit around the galaxy is incredibly orderly. It's nearly a perfect circle, and our speed is almost perfectly synced up with the rotation of the spiral arms themselves. Remember the traffic jam analogy? While other cars are constantly getting stuck in traffic, we're in a car on a clear service road, moving at the same speed as the jam. We're keeping pace with it, but from a safe distance, never getting caught in the chaos. We orbit in this protected zone, this cosmic safe lane, shielded from the frequent supernovae and gravitational mayhem of the major arms. We're in a cosmic sanctuary. Our existence isn't just about being on the right planet, at the right distance from the right star. It's also about having the right address, in the right neighborhood, within a city of billions of stars. We are here because we live in a quiet, protected corner of the galaxy. It's in this quiet, protected corner of the city that a thought can even arise. A thought about our universe, and how we share these journeys of scale and wonder. This exploration is only possible because of our collective human curiosity. If these trips into the grand design of our galaxy give you a sense of perspective and awe, consider becoming a part of the crew. By subscribing, you help us continue these journeys and keep charting the map of our unbelievable home, together. Now, let's continue our journey, leaving the safety of our arm and heading downtown, toward the city center. The galactic center. Our journey now takes us inward, toward the very heart of the Milky Way, a trip across 27,000 light-years of space. As we move, the view changes completely. The sparse scattering of stars in our neighborhood gives way to a sky that gets brighter and brighter. If you were to stand on a planet here, thousands of light-years closer to the center, the idea of a dark night sky would be meaningless. The sky would be a constant, blazing twilight, crowded with tens of thousands of stars, shining with the combined light of 100 full moons. The darkness we know is a feature of the suburbs. Here in the inner city, the light is overwhelming. And the stars themselves are different. They're older, ancient. In the spiral arms, we see the bright blue of young, hot stars. Here, the main colors are the yellow and red of ancient suns, stars that have been burning for 10 billion years or more. This is the Old City, the historical district, filled with the galaxy's first-generation residents. As we get closer, we see the heart of our galaxy isn't just a ball of stars. Like more than half of all spiral galaxies, the Milky Way has a huge, elongated bar of stars cutting through its core. It's a dense, tightly packed, cigar-shaped collection of hundreds of millions of ancient stars, all spinning together like a solid object. This is the downtown core, the massive hub that organizes the rest of the city. And there, at the absolute dead center of the bar, at the very center of our galaxy, is the final stop on our inward journey. A point known as Sagittarius A star. It's not a point of light, but a point of ultimate darkness. It is a supermassive black hole. This isn't like the black holes left when giant stars die. This is a monster on a whole other level. It has a mass more than 4 million times that of our Sun, all squeezed into a space smaller than Mercury's orbit. It is the gravitational anchor for our entire galaxy. Every single one of the hundreds of billions of stars you live inside, including our own Sun, is orbiting this single, invisible point. It is the silent, unseen ruler of the city. It doesn't shine, it consumes. It doesn't radiate, it commands. Its immense gravity warps space and time itself, creating a cosmic drain from which nothing, not even light, can escape. The stars closest to it are whipped around at incredible speeds, their frantic orbits proving the power of the unseen object they're tethered to. This is the engine at the heart of the metropolis, the central mystery our entire galactic city revolves around. The grand structure and mysteries. Now that we've seen the core, let's pull back one last time to see the whole city in a single view. From here, we can appreciate the full, majestic structure of our home. We see the brilliant, dense central bar. We see the great spiral arms unwinding from its ends, vast rivers of stars, gas, and dust, tracing a pinwheel pattern across 100,000 light-years of space. While it's been debated, the latest maps seem to confirm the Milky Way has 4 main spiral arms. The 2 biggest are the Scutum Centaurus arm and the Perseus arm, the dangerous highways we talked about. The other 2 major arms are the Norma arm and the Sagittarius arm. Our own Orion arm is now understood to be a smaller spur, like a bridge connecting the larger structures. But our galaxy still holds deep mysteries. One of the weirdest is a puzzle in its own structure. When astronomers map the galaxy using the light from old, red stars, they see a clear 2-armed spiral. But when they map it using the radio waves from gas clouds and the light of young, blue stars, they see 4 distinct arms. Why the galaxy looks different depending on what you're looking at is a puzzle we're still trying to solve. And there's another surprising detail about our own place in all this. Our solar system doesn't orbit the galaxy flat, like a record on a turntable. The plane of our solar system, the flat disk our planets orbit the Sun on, is tilted at a dramatic 60-degree angle to the plane of the galaxy itself. What's more, we're not perfectly in that galactic plane right now. At this point in our long history, we're located about 55 light-years above the galactic equator. This means as our solar system takes its grand tour around the galactic center, a trip that takes about 230 million years, we're also bobbing up and down, weaving through the galactic plane like a horse on a cosmic carousel. We pass through the dense middle of the galaxy, move high above it, then fall back down through it, over and over. We aren't just orbiting, we're dancing. This journey, one single lap around the galaxy, is called a galactic year. Since our Sun was born, it has made this trip only about 20 times. The last time our solar system was in this exact spot, dinosaurs were just beginning to walk the Earth. The entire span of human history has happened in a tiny fraction of a single galactic year. We are a momentary flicker in the long, slow life of our star, on its endless pilgrimage around the city of light. The reflective return. From the grand, sweeping view of the entire Milky Way, let's make our way home. We pull our focus back, past our neighbor Andromeda, and into the familiar spiral of our own galaxy. We fly past the blazing core and the silent, massive black hole at its heart. We cross the great, dangerous superhighways of the Perseus and Scutum Centaurus arms. We find our way back to the quieter districts, to the local spur we call the Orion arm. And within that arm, among its scattered stars, we search for one particular, average, yellow star. There it is, our Sun. One star among an estimated 100 to 400 billion others. A single, solitary point of light. We draw closer, past the ghostly comets of the Oort cloud, past the ice giants, past the rings of Saturn and the great red spot of Jupiter. We see a small, blue and white marble, orbiting in a warm, gentle sunbeam. We see our home, Earth. You are here. After this journey, the phrase feels different, doesn't it? Here is no longer just a planet. Here is a solar system, tilted at a jaunty angle, bobbing up and down through a minor spiral arm. Here is a cosmically protected neighborhood, a safe harbor in a city of beautiful chaos. Here is a place located 27,000 light-years from a supermassive black hole that holds it in a gentle, gravitational hug. Your home isn't just a rock. Your home is a galaxy. You are not just on a world, you are in a city. A city of incomprehensible scale and beauty, of violent creation and silent mysteries. Its light is the sky above you. Its dust is the material inside you. This is not a metaphor. It is a literal, physical truth. You live inside a city of hundreds of billions of stars. The giant invisible structure holding our galaxy hostage. We live on a tiny planet, orbiting an unremarkable star, tucked away in a quiet spiral arm of the Milky Way. We feel the ground beneath our feet as solid, our spot in the universe as a fixed point in the silent, static dark. But that feeling, that profound sense of stillness, is maybe the greatest illusion we've ever known. Because right now, you, this planet, our sun, and our entire galaxy are being pulled across the universe at over 2 million kilometers per hour. We aren't just drifting. We are being dragged by a structure so immense and a force so vast that for most of history, we had no idea it was even there. This isn't science fiction. This is the story of our cosmic predicament, and how we discovered that we're all passengers on a galactic vessel, with something immense and hidden dictating our course. Our local family. So, before we chase this colossal mystery into the dark, let's get our bearings. Let's draw a map, starting right at our front door. Our home, the Milky Way, is a breathtaking structure. It's a barred spiral galaxy, a swirling pinwheel of a few hundred billion stars, vast clouds of gas, and a halo of unseen dark matter that dwarfs everything we can see. Spanning 100,000 light-years across, it's a stellar metropolis, and our solar system is in its quiet suburbs, making one grand lap every 230 million years. It's easy to feel like this is our island universe, adrift and alone. But we're not alone. Our galaxy is part of a small, gravitationally bound collection called the local group. Think of it as our cosmic town, spanning about 10 million light-years and containing over 80 known galaxies. Most of these are small dwarf galaxies, like little celestial footnotes. But in this town, there are three titans that define the destiny of our entire neighborhood. First, there's the Milky Way. For a long time, we thought we were the biggest, but we now know we're number 2. The true heavyweight, the patriarch of this cosmic family, is the Andromeda galaxy. About 2.5 million light-years away, Andromeda is a monster, possibly containing as many as 1 trillion stars. On a clear, moonless night, you can just barely see it with your naked eye, a faint, fuzzy smudge in the sky. That smudge is the most distant object you'll ever see without a telescope. The third major player is the Triangulum galaxy, the smallest of the 3 spirals, but still a giant compared to the dwarfs. Together, the Milky Way and Andromeda act like 2 gravitational anchors for the whole group. But this family portrait isn't static. The 2 giants, Andromeda and the Milky Way, are rushing towards each other. They're locked in a gravitational embrace, closing the gap at a staggering 110 kilometers per second. This isn't a near miss. It's a head-on collision course. In about 4 to 5 billion years, our 2 majestic spirals will meet. It won't be a cataclysm of fire. The space between stars is so vast that direct collisions are incredibly rare. Instead, it will be a slow, gravitational dance over hundreds of millions of years. The galaxies will pass through each other, their spiral arms torn into great streams of stars. They'll fly apart, then get drawn back together, merging and melding until their spiral shapes are erased forever. What rises from the ashes will be a new, colossal galaxy that some astronomers have already nicknamed Milky Way. This is the ultimate fate of our local town. But even this epic collision is just a sideshow. It's a local event, dwarfed by a much larger, much more mysterious motion affecting everything for hundreds of millions of light years. The pull between the Milky Way and Andromeda is strong, but there's another pull, an external one, that is even stronger. The anomaly in the cosmic flow. For most of the 20th century, our understanding of the universe was simple. Everything is moving away from everything else. In the 1920s, Edwin Hubble discovered that distant galaxies have their light redshifted, meaning they were all receding from us. The farther away a galaxy was, the faster it was moving. This was the first real evidence that the universe is expanding, carrying galaxies along like raisins in a rising loaf of bread. This gave astronomers a baseline, a predictable cosmic flow. But to measure that, you need a fixed reference point. That backdrop was discovered by accident in the 1960s by two engineers, Arno Penzias and Robert Wilson. They were trying to get rid of a persistent hiss in a radio antenna. No matter where they pointed it, this faint microwave signal was there. That hiss turned out to be the afterglow of the Big Bang itself. The cosmic microwave background, or CMB. The CMB is the faint, residual heat from the creation of the universe, and it's almost perfectly uniform in every direction. It provides the ultimate frame of reference, the rest frame of the universe. By measuring tiny temperature variations in the CMB, we can clock our own speed relative to the universe's expansion. And when astronomers did this, they found something startling. We have what's called a peculiar velocity, a motion that's asterisk on top of the general expansion. After accounting for every other motion, a clear picture emerged. Our entire Milky Way galaxy, and our whole local group, is being pulled through space at a stunning speed of around 600 kilometers per second. This was the first real clue. The smooth, predictable expansion of the universe was being violated right here in our cosmic neighborhood. Something, somewhere out there in the dark, was powerful enough to drag entire groups of galaxies off their expected course. Astronomers now knew which way we were being pulled. The question was, what was doing the pulling? The hunt for this great attractor had begun. Peering through the veil, the direction of our motion was clear. Towards the southern sky, near the constellations Centaurus and Norma. The logical step was to point our telescopes there and see what was up. Surely something massive enough to pull galaxies would be obvious. But when astronomers looked, they saw almost nothing. They had run headlong into the most frustrating obstacle in astronomy, our own galaxy. The plane of the Milky Way is thick with stars, gas, and opaque lanes of dust. This band acts like a curtain, blocking our view of the distant universe behind it. Astronomers call it the zone of avoidance, because, for centuries, they just avoided looking there. And as luck would have it, the great attractor was located right behind the densest part of it. Visible light telescopes were useless. So astronomers turned to other forms of light that could pierce the veil. Radio waves, with their longer wavelengths, aren't easily absorbed by dust. In the 1980s, a team of astronomers, famously known as the Seven Samurai, surveyed hundreds of galaxies, measuring their distances and peculiar velocities. Their work confirmed it. Not only was our local group being pulled, but so were our neighboring galaxy clusters, all flowing in the same direction, towards the same hidden point. Next came infrared and X-ray astronomy. Infrared light can also punch through dust, and surveys began to catalog galaxies hidden in the zone of avoidance. At the same time, X-ray telescopes looked for the telltale glow of massive galaxy clusters, which are filled with superheated gas that shines brightly in X-rays. As data from all these different wavelengths poured in, the picture sharpened. Piece by piece, astronomers were mapping a previously unseen landscape. The veil was being lifted, and what lay behind it was more magnificent than anyone had anticipated. The first revelation. The Great Attractor. As the maps grew more detailed, the prime suspect emerged from the haze. The mysterious pull wasn't coming from a single object, like some physically impossible black hole. The truth was both more mundane and more awe-inspiring. The Great Attractor was a place, not a thing. It's a vast region of space where the density of matter is unusually high. At its heart, located roughly 150 to 250 million light-years away, was the Norma cluster, a massive supercluster of galaxies. Here, thousands of galaxies were packed together, their combined mass creating a deep gravitational well in spacetime. We, along with our local group and all our neighbors, were sliding down the edge of that well. This seemed to be the smoking gun. Here was a concentration of matter large enough to explain the peculiar velocity that had puzzled astronomers for decades. The mystery of the Great Attractor appeared to be solved. It was this massive collection of galaxies, hiding behind the glare of our own Milky Way. For a while, this was the accepted answer. It was a neat and tidy solution. We had found the culprit, mapped its location, and understood its nature. The story, it seemed, was over. But that's not the whole story. As is so often the case in science, solving one mystery just opened the door to a much bigger one. Astronomers soon noticed something odd. The Great Attractor, this massive structure that was pulling us, was itself being pulled by something else. The first revelation wasn't the end of the story, it was a plot twist. The structure holding us hostage was itself just a prisoner of something even bigger. The grand scale and the Laniakea supercluster. The discovery that the Great Attractor was also in motion was a shock. It was like finding out the giant magnet pulling your compass is itself being dragged by an even bigger magnet. The investigation had to zoom out dramatically. The breakthrough came from a new way of looking at the universe. Instead of just mapping where galaxies are, a team led by R. Brent Tully began to map how they move. By analyzing the peculiar velocities of tens of thousands of galaxies, they created a topographical map of cosmic gravity, tracing the basins and watersheds that define the cosmos. What they unveiled in 2014 was breathtaking. The Great Attractor wasn't a final destination. It was just the gravitational center of an unimaginably vast structure that contained our own galaxy and everything we had ever known. They named it the Laniakea supercluster. Laniakea is Hawaiian for immense heaven, and it's no exaggeration. The Laniakea supercluster is over 520 million light-years across and contains more than 100,000 galaxies, all bound together in a single, flowing structure, with the mass of 100,000 trillion suns. For decades, we thought we were part of the Virgo supercluster. But the discovery of Laniakea revealed that the Virgo supercluster is just a small suburb of our true home continent. The boundary of Laniakea is defined by motion. Every galaxy inside the boundary is flowing inwards toward a common center, the Great Attractor. Every galaxy outside the boundary is flowing away, toward some other structure. We are all flowing down the same cosmic river. This revealed the true nature of the universe. On the largest scales, it looks like a giant, intricate, cosmic web. It's made of vast filaments of galaxies and dark matter, and where these filaments intersect, they form dense knots, the great clusters. In between are enormous, empty voids. Laniakea is one massive region of this web, a convergence of several filaments. We aren't being pulled by a single object. We are flowing along the very structure of the universe itself. The giant invisible structure is Laniakea. But there's one final, mind-bending twist. Our entire supercluster, this immense continent of galaxies, is also on the move. Laniakea itself appears to be flowing towards an even larger concentration of mass known as the Shapley supercluster, about 650 million light-years away. Our cosmic river might just be a tributary of an even larger river, leading to an even deeper cosmic sea. Our cosmic destiny revisited. So, with this grand new map, let's zoom back into our own backyard and reconsider our fate. What does being in the Laniakea flow mean for the impending collision between the Milky Way and Andromeda? Think of the Laniakea flow as a large-scale ocean current, gently carrying our entire local group along. The collision with Andromeda, meanwhile, is a local drama, a powerful whirlpool within that current driven by the two galaxies themselves. As our two galaxies continue their journey within Laniakea, they are also continuing their personal journey toward one another. In about 4 to 5 billion years, the collision is set to begin. The night sky on a future Earth will be transformed. Andromeda will grow from a faint smudge into a magnificent spiral filling a huge portion of the sky. Then the dance begins. As the galaxies first pass through each other, tidal forces will tear long arcs of stars and gas from their outer edges. Gravity will compress the gas clouds, triggering a spectacular burst of star formation. The sky will light up with millions of brilliant newborn stars and glowing pink nebulae in a galactic firestorm. After the first pass, the galaxy's cores will continue on, but gravity will pull them back for a second, then a third encounter. Over hundreds of millions of years, the elegant spirals will be completely erased. The stars of both galaxies will be mixed and blended, eventually settling into a new, randomized, football-like shape. Milkomeda will be a giant, quiet, elliptical galaxy, a monument to the two vibrant spirals that created it. This is our destiny. Consolidation. It's a process happening all over the universe as gravity constantly pulls things together. Our journey from our quiet solar system to the staggering scale of Laniakea shows a universe that's more interconnected and dynamic than we ever imagined. Every discovery just seems to peel back one more layer of a truly infinite cosmic onion. If you enjoyed this journey into the vast, invisible structures that shape our destiny, consider subscribing and join us for our next expedition into the unknown. We started with a simple, unsettling fact. You are not still. You are hurtling through space, caught in a cosmic current. We followed the mystery of that motion, from the discovery of our peculiar velocity, through the frustrating search behind the zone of avoidance, to the revelation of the great attractor, which turned out to be just a waypoint. And finally, we arrived at our new cosmic address. A small corner of the immense, flowing structure of Laniakea, our home supercluster of 100,000 galaxies. We now see we're not being held hostage. We are an integral part of the universe's grand design. We're like a single water molecule in a vast river, flowing along channels carved by gravity since the beginning of time. Our motion isn't a predicament, it's participation. And while we now have a name for our home, Laniakea, the journey of discovery is far from over. What lies beyond Shapley? What other invisible structures govern the universe on even larger scales? Our map has gotten bigger, but the sense of awe and the endless horizon of mystery remains. And maybe that's the most profound revelation of all. We live inside a giant glowing web. For all of human history, we've seen the universe as a vast, dark canvas sprinkled with brilliant, solitary islands of light. We told ourselves a story of cosmic grandeur, sure, but also one of profound randomness, a story of a cosmos born in a chaotic explosion and left to the haphazard pull of gravity. It's a story of isolation. Each galaxy, a lonely ship sailing an endless, empty ocean. Each star, a distant campfire we can see but never feel. It's a beautiful picture. And it's almost completely wrong. What if that chaos is just a grand illusion? What if the randomness we see is simply a failure of perspective, like staring at a single pixel and trying to understand a masterpiece? Tonight, we're going on a journey to the very edge of the known universe to reveal a hidden architecture, an unseen order that connects everything. Because our home, our galaxy, the Milky Way, is not a lonely island at all. It's a single, glowing node in a colossal, interconnected web that stretches across the entire universe. This is the story of the cosmic web, the largest structure we know of, and our true place within it. The birth of a new cosmology. For most of the 20th century, our best model of the universe was one of large-scale uniformity. Once we accepted that our sun wasn't the center of the galaxy, and our galaxy wasn't the center of the universe, we settled on an idea called the cosmological principle. Put simply, it says that on big enough scales, the universe should look pretty much the same everywhere, and in every direction. No special places, no cosmic continents or oceans, just an endless, uniform mist of galaxies. This idea made a lot of sense. It was the logical next step after knocking ourselves off the cosmic pedestal. And for a while, the evidence seemed to back it up. When astronomers pointed their telescopes at the sky, they saw galaxies and galaxy clusters, but their distribution looked more or less random, like salt sprinkled on a dark tablecloth. Sure, you might find a few clumps, but zoom out far enough, and it all evens out. The universe was thought to be a smooth soup of matter, gently expanding since the dawn of time. But science is all about poking at comfortable ideas until they break. And in the late 1970s and 1980s, the first cracks in this smooth soup cosmology started to appear. A team of pioneers at the Harvard-Smithsonian Center for Astrophysics, people like Margaret Geller, John Huchra, and Valerie de la Parent, began what seemed like a simple project: mapping the CFA redshift survey. Their goal was straightforward: map the positions of galaxies in 3D. They measured a galaxy's two-dimensional position on the sky, that's the easy part, and then they measured its redshift. Redshift is what happens when light from a distant object gets stretched to longer, redder wavelengths as the space between it and us expands. Thanks to Hubble's law, this redshift gives a reliable estimate of distance. Combine position and distance, and you get a 3D map of our little corner of the universe. The first survey, finished in 1982, already hinted that the universe wasn't as smooth as everyone thought. It showed galaxies and clusters were part of some kind of filamentary network. But it was the second survey, CFA2, that delivered the real shock. As they plotted the data, slice by slice, they weren't seeing a random spray of points. They were seeing something else entirely. In 1986, they published a paper called "A Slice of the Universe," with an image that would forever change how we see the cosmos. Instead of an even distribution, the galaxies were arranged in shocking patterns. They formed long, thin strands and dense, clumpy walls, surrounding vast, dark regions that were almost completely empty. One of the most famous and surprising discoveries was a shape astronomers nicknamed the Stickman, a pattern of galaxies that looked uncannily like a child's drawing. It was a cosmic Rorschach test, of course, a chance alignment. But it was proof that structure existed on scales far larger than anyone had imagined. Then, in 1989, they found something that tore the old picture of the universe to shreds. Stretching across their survey map was an immense, connected sheet of galaxies, a structure so vast it was named the Great Wall. This wasn't just a cluster, or even a supercluster. It was a coherent structure of thousands of galaxies stretching over 500 million light-years across the sky. Its size was simply staggering, far too big to be explained by the models of gravity at the time. The smooth, uniform soup was gone. The random spray of stars was an illusion. In its place was something far more intricate, more organized, and infinitely more mysterious. Geller and Huckra's work was the first hard evidence that the universe has a skeleton. They hadn't just mapped the stars, they had stumbled upon the first threads of the cosmic web. The journey to understand this incredible structure was just getting started. Our cosmic address. A journey from home. To really get a feel for the cosmic web, we have to start where we are and zoom out, step by step, until the whole thing is revealed. It's a journey of escalating perspective, from the familiar to the truly incomprehensible. Our journey begins at home, on a small, rocky planet orbiting an unremarkable star, tucked away in a spiral arm of a galaxy we call the Milky Way. Our galaxy is a vast, spinning disk of anywhere from 100 to 400 billion stars, a city of light about 100,000 light-years across. But it's not alone. The Milky Way is one of the two biggest members of a small galactic family called the Local Group. Our dominant neighbor is the Great Andromeda Galaxy, and together with the Triangulum Galaxy and about 80 smaller dwarf galaxies, we form a gravitationally bound family, all dancing around a common center of mass. But this cozy family is on the move. The entire Local Group is hurtling through intergalactic space at around 600 kilometers every second. That's over 2 million kilometers per hour. So what's pulling us? Where are we going? To find out, we have to zoom out again. About 50 to 60 million light-years away lies our nearest metropolis of galaxies, the Virgo cluster. If our Local Group is a quiet cul-de-sac, the Virgo cluster is a bustling, chaotic downtown core. It contains over 300 maybe even 2,000 galaxies packed into a region just 10 million light-years across. Unlike our peaceful Local Group, Virgo is a violent place. It's dominated by giant elliptical galaxies, old galactic cannibals that grew enormous by eating their smaller neighbors. At its heart lies the monster galaxy Messier 87, a behemoth with trillions of stars, famous for the supermassive black hole whose shadow we've actually managed to photograph. The intense gravity of the Virgo cluster acts as a powerful beacon. It's the main gravitational force in our immediate neighborhood, and it's the primary reason we're moving so fast. The Local Group is falling towards the Virgo cluster, pulled in by its immense mass. But even that isn't the whole story. Virgo itself is just one piece of an even bigger structure. Let's zoom out one more time. The Virgo cluster, our own Local Group, and about 100 other galaxy groups and clusters are all part of a single, colossal entity. In 2014, a team led by Brent Tully mapped not just where galaxies were, but where they were going. They found that all of these smaller groups, spread across more than 500 million light-years, were all flowing toward a common point. They named this entire cosmic watershed our home supercluster, Laniakea, a Hawaiian name meaning immense heaven. Laniakea contains around 100,000 galaxies, with a total mass of about 100 quadrillion suns. Our Milky Way is just a tiny speck on its distant outskirts. The Virgo cluster, which once seemed like the center of our universe, is just one neighborhood in this vast city. The galaxies of Laniakea flow along streams, like rivers emptying into an ocean, all converging on a region called the Great Attractor. For decades, the Great Attractor was a huge mystery. We knew there was a massive gravitational pull coming from about 150 to 250 million light-years away, in the direction of the Norma constellation. The problem was, this region is right behind the plane of our own Milky Way, in an area called the zone of avoidance. The thick gas, dust, and stars of our own galaxy act like a screen, blocking our view. We could feel its pull, but we couldn't see what it was. Thanks to X-ray and radio telescopes that can peer through the dust, we now know the Great Attractor isn't some weird, singular object. It's simply a gravitational focal point dominated by a massive galaxy cluster called the Norma cluster. This cluster is the gravitational heart of our Laniakea supercluster. And yet, here's the mind-bending twist. Despite its incredible size, Laniakea isn't really a structure in the way a galaxy is. It's not gravitationally bound. The force that's winning on the largest scales is the accelerating expansion of the universe, driven by what we call dark energy. While Laniakea's gravity can pull galaxies into a collective flow, it's not strong enough to win against cosmic expansion. Our immense heaven is being torn apart. The different parts of Laniakea are accelerating away from each other, destined to scatter. We live in a temporary, dissolving city of stars. We will never reach the great attractor. This journey reveals a fundamental truth. The universe is a dynamic dance between forces. Gravity gathers matter into amazing structures, while dark energy relentlessly pulls them apart. And Laniakea, our home, is just one node in a network that extends far beyond what we can see. The scaffolding of the cosmos. Now that we've mapped our local neighborhood, it's time to zoom out one last time, to see Laniakea not as the final picture, but as a single point of light in a much larger tapestry. So, what connects Laniakea to other superclusters like Shapley, Hercules, or Perseus Pisces? The answer lies in the parts that make up the cosmic web itself, the filaments and the voids. Picture the universe as a three-dimensional spiderweb. The dense, glittering junctions where threads meet are the galaxy clusters and superclusters, the cosmic cities like Virgo. Connecting these bright nodes are the filaments. These are the true highways of the cosmos. Galaxy filaments are immense, thread-like formations of galaxies, gas, and dark matter that can stretch for hundreds of millions, sometimes even billions, of light years. While incredibly long, they're relatively thin, maybe only 20 million light years across. These are the walls and bridges that outline the grand structure of the universe. Some are so huge they get names, like the CFA2 Great Wall that first shocked astronomers, or the Sloan Great Wall, which is nearly 1.4 billion light years long. The largest potential structure ever found, the Hercules Corona Borealis Great Wall, might span a mind-boggling 10 billion light years, though its existence as a single structure is still up for debate. But what are these filaments made of? They aren't just strings of galaxies. In fact, the galaxies we see are just the glowing decorations. Most of the mass in these filaments, about 5/6 of it, is the mysterious, invisible stuff we call dark matter. Dark matter forms the underlying scaffolding of the universe. It doesn't interact with light, but its gravity is what shapes everything we see. Laced within this dark matter skeleton is the normal matter. A tiny fraction of it has condensed into the galaxies that light up the filaments like beads on a string. But most of it, over half of all the normal matter created in the Big Bang, exists as a vast, thin sea of gas flowing along these cosmic rivers. For years, this gas was the answer to the missing baryon problem. Astronomers knew a certain amount of normal matter should exist, but they couldn't find it all in stars and galaxies. Now we know it was hiding in the filaments. This gas isn't just sitting there. It's the lifeblood of the universe, flowing down the filaments into galaxy clusters, providing the raw fuel for new stars and galaxies to form. If the filaments are the bridges and the clusters are the cities, the final component is the vast emptiness between them. The cosmic voids. These aren't just empty spaces, they are a dominant feature of the cosmos. Voids are enormous, roughly spherical bubbles of near emptiness, hundreds of millions of light years across. They are so empty that they make up about 80% of the volume of the universe. By volume, our universe is mostly void. Our own Milky Way sits on the edge of one called the local void. When we look in the direction opposite the Virgo cluster, we're staring into a profound emptiness. Voids are regions where the early universe was slightly less dense than average. While the denser regions collapsed under gravity to form filaments and clusters, the underdense regions did the opposite. They expanded, hollowing out and pushing matter toward their edges, like rising dough creating bubbles in a loaf of bread. Life for a galaxy inside a void is very different. Studies show that void galaxies evolve much more slowly. They're isolated, shielded from the violent collisions and mergers common in clusters. As a result, void galaxies tend to be younger, bluer, and more actively forming stars. They're the quiet, pristine countryside of the cosmos. The interplay of dense clusters, connecting filaments, and vast voids creates the sponge-like, foamy structure of the universe we call the cosmic web. It's a structure of breathtaking scale, all born from the tiniest of whispers at the dawn of time. The blueprint of creation. So how does such a monumental structure even come to be? The origin of the cosmic web is one of the greatest triumphs of modern cosmology, a story that connects the smallest possible scales to the largest imaginable ones. The blueprint was written in the first fraction of a second after the Big Bang. In the very beginning, the universe was an incredibly hot, dense, nearly uniform sea of energy. Nearly uniform. Thanks to quantum mechanics, even a perfect vacuum isn't truly empty. It's a roiling soup of tiny energy fluctuations. During a period called cosmic inflation, the universe expanded exponentially, stretching those tiny, fleeting quantum wobbles to astronomical scales. What were once microscopic fluctuations became vast regions of slightly higher or lower density. These tiny variations, just 1 part in 100,000, were the seeds of all future structure. We can still see the imprint of these seeds today, frozen onto the oldest light in the universe. The cosmic microwave background. After inflation, the universe was filled with a hot plasma of normal matter, radiation, and of course, dark matter. For a few 100,000 years, the normal matter was locked in a cosmic battle. The intense pressure from light pushed back against gravity. But dark matter, which doesn't interact with light, was immune. It only felt gravity. So, in the regions that were slightly denser, the dark matter immediately began to clump together, forming invisible wells of gravity. About 380,000 years after the Big Bang, the universe cooled enough for light to break free. The pressure was released, and normal matter was finally free to fall into the gravitational wells that the dark matter had already been digging. What followed was a 13.8 billion year construction project. The regions of highest density pulled in more and more matter, becoming the future sites of massive galaxy clusters. But things didn't just clump. A slightly squashed, oval-shaped region would collapse fastest along its shortest axis first, forming a flat pancake. This sheet would then collapse along its next shortest axis to form a long, thin filament. Finally, the filament itself would break up into the clumps that became galaxies. This model, known as the Zeldovich pancake model, beautifully shows how this web-like structure forms naturally. Meanwhile, the regions with the lowest density had the opposite fate. As matter flowed away from them and into the filaments, they became emptier and emptier, expanding to become the great cosmic voids. To test this theory, cosmologists run massive supercomputer simulations. Projects like Illustris TNG and Millennium TNG start with the known initial conditions of the universe, the laws of physics, the amounts of dark matter and dark energy, and those tiny density fluctuations, and let gravity do its work for 13.8 billion simulated years. The results are astonishing. Without being told to, the computers generate a universe that looks remarkably like our own, complete with a vast, foamy network of clusters, filaments, and voids. These simulations give us incredible confidence that our story of the cosmic web's formation from quantum seeds to galactic superstructures is fundamentally correct. It's a structure sketched by quantum physics, built by gravity, and painted on a canvas of dark matter. The edge of everything. We've journeyed from our home planet to the heart of our supercluster, and from there to the vast architecture of the cosmic web. This brings us to a final, profound question. Does this web go on forever? Is there an edge to the universe? The answer is both simple and incredibly complex, and it comes down to the difference between the asterisk universe and the asterisk observable universe. The universe itself might very well be infinite. Based on our best measurements, space appears to be flat, which means it could stretch on forever. If you started traveling in one direction, you would probably travel forever. However, the part of the universe we can see is finite. This is the observable universe, and its boundary is called the particle horizon. This isn't a physical wall you could crash into. It's a horizon in asterisk time. The universe is about 13.8 billion years old. That means light from the most distant objects has had, at most, 13.8 billion years to travel to our telescopes. Anything whose light would take longer than that to reach us is, for now, beyond our view. You might think that means the observable universe is a sphere with a radius of 13.8 billion light-years. But remember, while that light was traveling, space itself was expanding. The galaxy that emitted the light we see today from the edge was much closer when the light began its journey. Factoring in that expansion, the actual distance to the edge of the observable universe today is about 46.5 billion light-years in every direction. So, what's out there, right at the edge? We're looking back to the dawn of time. The light from that boundary was emitted just after the Big Bang, when the universe was still a hot, opaque plasma. We see this ancient light today as the cosmic microwave background. As we look out in space, we look back in time, and the cosmic web appears younger and less developed, dissolving into a more uniform, primordial state. But there's another twist, thanks to dark energy. The expansion of the universe is accelerating. This creates another, even more restrictive boundary called the cosmic event horizon. This is the point of no return. Because space is expanding faster and faster, there are distant galaxies receding from us at speeds greater than the speed of light. This doesn't violate relativity. The galaxies aren't moving through space that fast, but the space between us and them is stretching that quickly. Any light emitted today by a galaxy beyond this event horizon, currently about 16 billion light-years away, will never reach us. The space between us is expanding so fast that the light is like a swimmer trying to cross a river flowing faster than they can swim. They make progress relative to the water, but they're still carried away from the opposite bank. These galaxies are being erased from our future. As the eons pass, the accelerating expansion will push more and more galaxies beyond our event horizon. The great superclusters we see today will wink out of sight. Even the other members of our Laniakea supercluster will eventually be carried away. Far in the future, observers in our galaxy will look out and see an almost entirely empty universe. The only galaxies left will be the ones that have merged with the Milky Way to form one giant, Milkomeda, galaxy. All evidence of the grand cosmic web, all the majestic filaments and superclusters, will have been stretched beyond the horizon, lost to the eternal darkness. We are living in an incredibly special moment in cosmic history. We might be the only generation of intelligent beings who will ever see the cosmic web in its full glory before dark energy tears it all apart. This journey to understand this structure is one of the greatest detective stories in science. If this tour of the cosmos has left you as awestruck as we are, consider subscribing and joining us as we keep exploring the biggest questions in the universe. What other hidden structures do you think are out there? Let us know in the comments. We've journeyed across billions of light-years, from the illusion of a random cosmos to the reality of an intricate, interconnected web. We've learned that we aren't adrift in a meaningless void, but are part of a structure so vast it's hard to wrap your head around. Our home is Laniakea, a temporary city of 100,000 galaxies flowing toward a great gravitational basin. And this city is just one bright node in a universe-spanning network of dark matter filaments and cavernous voids, born from quantum flickers at the dawn of time. This web is not static. It's a living architecture, constantly being built up by gravity and torn apart by dark energy. The galaxies inside it are shaped by their environment, evolving peacefully in the quiet of the voids or violently in the chaos of the clusters. And we've looked to the very edge of what we can see, the particle horizon, a boundary in time that separates our known universe from the vast, unknown cosmos beyond. The story of the cosmic web reframes our existence, not as one of cosmic isolation, but of profound connection. Every atom in our bodies was forged in a star, that star was born in a galaxy, that galaxy was fed by a filament, and that filament is part of a web that encompasses everything. We aren't just observers of the universe. We are a part of its grand and glowing structure. And the quest to map its threads and plumb its voids continues. The web is still full of mysteries, and its story is still being written in the stars. The man who discovered the universe is stretching. For almost all of human history, we looked up at the night sky and saw a universe that was beautiful, eternal, and comfortingly small. Our ancestors told stories about the constellations, our philosophers debated the nature of the heavens, and our earliest scientists mapped the stars. But through it all, one belief remained constant. The universe was a quiet, static place. It was just our own Milky Way galaxy, a single island of stars in an endless, empty ocean. Everything we could see was believed to be part of our cosmic home. The universe had an edge, and we were it. But in the 1920s, one man, armed with the world's most powerful telescope and a relentless curiosity, would shatter that reality forever. He would take that cozy image of the universe and tear it to shreds, revealing a cosmos more vast, violent, and bizarre than anyone had ever dared to imagine. This is the story of Edwin Hubble, the man who discovered that the universe is not only bigger than we thought but is also stretching the very fabric of space in all directions. This is the story of the moment our reality broke wide open. A universe in a bottle. To really get the seismic shock of Hubble's discovery, you have to go back to a time when the word galaxy only meant one thing: our own. The scientific consensus was that the Milky Way was the entirety of creation. A grand city of stars, for sure, but a city with walls. Beyond it lay nothing but an infinite void. This wasn't just a popular idea. It was the bedrock of cosmology. Even the great Albert Einstein, whose theory of general relativity was published in 1915, believed in this static universe. The funny thing is, his own equations told him otherwise. When he first formulated them, he was disturbed to find they predicted a dynamic universe, one that should be either expanding or collapsing under its own gravity. A stable, unchanging cosmos was impossible according to his own math. This was so philosophically unsettling that Einstein figured he must have made a mistake. So, he introduced a fudge factor, a new term he called the cosmological constant. It was a bit of mathematical scaffolding designed for one purpose: to hold the universe still. He would later call this his biggest blunder, but at the time, it felt necessary to preserve the known world. The scientific community was so dug in that in 1920, the stage was set for one of the most famous showdowns in the history of science, the Great Debate. Held at the Smithsonian Museum of Natural History, it pitted two brilliant astronomers against each other to argue over the very scale of the universe. On one side was Harlow Shapley. A charismatic and formidable astronomer, Shapley was the champion of the big galaxy model. He had recently done groundbreaking work that radically increased the estimated size of the Milky Way, arguing it was a colossal structure, perhaps 300,000 light-years across. Because it was so enormous, he reasoned, everything we saw in the sky must be inside it. This included the mysterious, spiral nebulae, faint, swirling clouds of light like the one in Andromeda. To Shapley, these weren't distant star systems, but gas clouds or new solar systems forming inside our own galaxy. For Shapley, the Milky Way was the universe. On the other side stood Eber Curtis, a quieter but equally respected astronomer. Curtis was pushing for a far grander, more terrifying vision: the island universes hypothesis. He believed that our Milky Way was just one galaxy among many, maybe millions. Those spiral nebulae, he argued, weren't local gas clouds at all. They were unimaginably distant island universes, entire galaxies just like ours, millions of light years away. His universe wasn't a single city of stars, but a massive archipelago of them, stretching into infinity. The debate was passionate, technical, and ultimately, a draw. Both men had valid points. Shapley was right about the immense scale of the Milky Way, and Curtis had compelling arguments about the nebulae. But neither could deliver a knockout blow because they lacked one crucial piece of evidence: a reliable way to measure the distance to these faint, fuzzy patches of light. Without a cosmic yardstick, the true scale of the universe would remain a matter of opinion. The debate ended in a stalemate. The key to breaking this deadlock was perched high above Pasadena, California. On the summit of Mount Wilson sat the most ambitious scientific instrument ever built, the 100-inch Hooker telescope. It was a titan of engineering. Its main mirror, a colossal piece of glass weighing over 4 tons, had been hauled up the winding mountain road and represented a quantum leap in astronomical power. For the first time, humanity had an eye sharp enough to potentially settle the debate. And arriving at Mount Wilson in 1919 was the man destined to wield it. His name was Edwin Hubble. Hubble wasn't your typical academic. He was a man of contrasts, a former lawyer who ditched a comfortable career to chase the stars, an accomplished athlete, and a decorated veteran of World War I. He spoke with a polished English accent, smoked a pipe, and carried an air of supreme confidence. He was meticulous, patient, and obsessive. He was the right man, in the right place, at the right time, holding the key to a door that would open onto a universe no one had ever imagined. A new cosmic yardstick and a stretching spectrum. Hubble's first great task was to settle the great debate. He aimed the massive Hooker telescope at the prime suspect, the great Andromeda Nebula. Was it a gas cloud in our cosmic backyard, or a majestic island universe? To find out, he needed that cosmic yardstick. Fortunately, the theory behind that yardstick had already been figured out, not by a famous astronomer, but by a quiet, unassuming woman working at the Harvard College Observatory named Henrietta Swan Leavitt. Leavitt was one of the Harvard computers, a group of women hired to do the painstaking work of analyzing data from photographic plates. While studying a class of stars known as Cepheid variables, she noticed something incredible. These stars weren't just dots. They pulsed, brightening and dimming with a precise, clockwork rhythm. And Leavitt discovered the secret. The longer it took for a Cepheid to pulse, the greater its true, intrinsic brightness was. This was the breakthrough everyone was waiting for. This period luminosity relationship turned these blinking stars into perfect, standard candles. Think of it like this. Imagine seeing a row of 100-watt light bulbs stretching down a dark street. You know they all have the same true brightness. So, the ones that look dimmest must be the farthest away. Leavitt's discovery meant that if you could find a Cepheid, you could measure its pulse, know its true wattage, and then calculate its distance by seeing how dim it appeared. Hubble knew that finding a Cepheid in Andromeda would be the smoking gun. Night after night, he photographed the nebula, exposing fragile glass plates for hours at a time. He would then spend his days hunched over the plates with a blink comparator, searching for any tiny dot of light that changed brightness. For months, nothing. Then, on October 5, 1923, he captured a plate that would change the world. He found what he first thought was a nova, a star flaring up. But as he compared it to older plates, he realized this star was appearing and disappearing. It was pulsing. It was a variable star. In a legendary moment, he crossed out the N for nova on the plate and scribbled VAR. He had found his prize. The calculation was next. He measured the Cepheid's pulse, used Leavitt's law to find its true brightness, and then compared that to how dim it looked from Earth. The number he came up with was staggering. The Cepheid, and therefore the Andromeda Nebula, was roughly 930,000 light-years away. Later, better measurements would push this to over 2.5 million light-years. The implications were profound. Shapley's biggest estimate for the Milky Way was 300,000 light-years across. This object was 3 times farther away than the most distant edge of our own galaxy. It wasn't a gas cloud. It was an island universe. A galaxy. Curtis had been right. The great debate was over. Hubble had single-handedly broken down the walls of our cosmic prison. The universe wasn't one galaxy, it was a cosmos filled with them. But this was only his first great revolution. The second would be even bigger. With the existence of other galaxies established, Hubble turned to another puzzle. Years earlier, an astronomer named Vesto Slipher had been measuring not distance, but motion. Using spectroscopy, he broke down the light from the spiral nebulae into a rainbow of colors. But this rainbow was crossed by dark lines, the spectral fingerprints of chemical elements. Slipher found something bizarre. For nearly every nebula he observed, these fingerprints were not where they should be. They were all shifted toward the red end of the spectrum. This phenomenon was called redshift. Think of the Doppler effect with an ambulance siren. As it races towards you, the pitch is high. As it speeds away, the pitch drops. Light does the same thing. Light from an object moving away from you gets stretched, shifting its color towards red, a redshift. What Slipher had found was that almost every galaxy seemed to be screaming away from us at incredible speeds. It was a strange result, and no one knew what to make of it. This is where Hubble, now armed with his new cosmic yardstick, came in. He realized he was in a unique position. He could find a galaxy's distance using Cepheids, and he could find its speed using redshift. He had 2 crucial data points for each galaxy. So he started plotting. On a piece of graph paper, he put distance on one axis and speed on the other. As he added more and more galaxies to the chart, a pattern emerged. It wasn't random. It was a straight line. The relationship was shockingly simple. The farther away a galaxy was, the faster it was moving away from us. A galaxy twice as far away was receding twice as fast. In 1929, he published his seminal paper, codifying this into a powerful equation. Velocity equals h0 times distance. This became known as Hubble's law. The implication was the most revolutionary idea since we learned the Earth wasn't the center of everything. The galaxies weren't just flying away from us. The law implied that the very fabric of spacetime itself was expanding. This brings us to the most famous analogy in cosmology: the balloon. Imagine you draw a bunch of dots on a balloon, each one a galaxy. Now, start inflating it. As the rubber stretches, what happens? From the perspective of any single dot, all the other dots appear to be moving away. And a dot far away moves away much faster than a dot nearby, because there's more stretching balloon between them. This is what Hubble had found. The galaxies aren't shrapnel flying through a static space. The space between the galaxies is what's stretching, carrying them along for the ride like raisins in a rising loaf of bread. This also explains why we seem to be at the center of it all. We're not. An observer in any galaxy would see the exact same thing. There is no center. It's happening everywhere. The universe wasn't a static stage. It was a dynamic, growing, stretching entity. A new reality. The discovery that the universe is expanding didn't just add a new fact to the textbook. It rewrote the history and future of everything. The most profound implication is what happens when you run the clock backward. If everything is moving apart now, then in the past, everything must have been closer together. Imagine the expanding universe as a movie. If you rewind that movie, the galaxies rush back toward each other. The space between them shrinks. The farther back you go, the smaller, denser, and hotter the entire universe becomes. Rewind all the way, and every star, every galaxy, all of it converges into a single, infinitesimally small, unimaginably hot and dense point. This was the first real evidence for an idea proposed a few years earlier by a Belgian priest and physicist named Georges Lemaitre. Working from Einstein's equations, Lemaitre had theorized that the universe began with the expansion of a primeval atom. Hubble's observations turned this from a mathematical curiosity into a testable scientific theory. Today, we call it the Big Bang. Hubble had, in effect, discovered the echo of creation. Interestingly, Hubble himself was famously hesitant to make this leap. He was an observer, a pragmatist. He cautiously referred to the redshifts as apparent velocities, worried it might be some new law of physics that just made light lose energy over vast distances. But as the evidence mounted, the expanding universe became undeniable. Hubble's law also gave us an audacious new tool, a way to estimate the age of the universe. If you know how fast things are moving apart and how far apart they are, you can calculate how long it took them to get there. The inverse of the Hubble constant gives you the time since the expansion began. His initial calculations were tricky, suggesting the universe was only 2 billion years old, which was a problem since geologists knew the Earth was much older. This age crisis was resolved over the following decades as astronomers discovered there were different types of Cepheid stars, refining the cosmic yardstick. With decades of work, we've arrived at our current best estimate. The Big Bang happened about 13.8 billion years ago. Hubble's work also set the stage for one of the most startling discoveries of the late 20th century. For decades, everyone assumed the expansion must be slowing down, thanks to the mutual gravity of all the galaxies acting as a brake. But in 1998, two teams of astronomers found the exact opposite. The expansion isn't slowing down. It's speeding up. About 5 billion years ago, some mysterious, anti-gravitational force we now call dark energy began to dominate the cosmos, pushing everything apart at an ever-increasing rate. We still don't know what it is, but it appears to make up nearly 70% of the universe. This is Edwin Hubble's ultimate legacy. The work he began is still going on, carried on by the instrument that bears his name, the Hubble Space Telescope. Launched in 1990, it has spent over 3 decades continuing his grand project, refining his constant, and confirming the accelerating universe. And now, its successor, the James Webb Space Telescope, is peering even further back toward the cosmic dawn. Every one of these great observatories stands on the shoulders of the man who first showed us the true, breathtaking scope of our reality. Before Edwin Hubble, our universe was a single room. We thought we knew its walls. With a few photographic plates and a revolutionary idea, Hubble didn't just find a new door in that room. He detonated the walls entirely, revealing our room was just one small house in an endless, expanding city of trillions. He gave us a new creation story, written not in myth, but in the language of shifting starlight, a story that begins 13.8 billion years ago and is still unfolding. He showed us that we are part of a grand, dynamic process, the stretching of space itself. He took us from a lonely, static universe and threw us into a cosmos that is vast, violent, and magnificent. Every time we look at a picture of a distant galaxy or contemplate the Big Bang, we are living in the universe that Edwin Hubble discovered. A universe that is still stretching, still evolving, and still full of mysteries, waiting for the next Hubble to come along and shatter our reality all over again. If you found this journey to the edge of reality as mind-bending as we did, make sure to subscribe and hit that notification bell so you don't miss our next cosmic exploration. This universe is full of stories, and we're here to tell them. Let us know in the comments. What cosmic mystery do you want us to tackle next? The shimmering wall at the end of space-time. What if you could travel to the very edge of space? Not to a wall of rock or ice, but to a place where all the stars have faded, and you find yourself staring at a soft, shimmering wall of light. This is the oldest light in existence, the afterglow of the Big Bang itself. It's the story of the cosmic particle horizon, the absolute limit of your vision, and the edge of everything you can ever know. This isn't a journey of speculation or fantasy. It's a journey into the heart of modern cosmology, to a boundary confirmed by our most powerful telescopes, a boundary made not of matter, but of time. We're going to travel there together, across unfathomable distances, to witness the birth of light and the dawn of transparency. This is the story of where our vision ends, and where the deepest mysteries of the cosmos begin. Imagine, for a moment, you're adrift in the deepest, blackest ocean you can think of. There's no up, no down, only a velvet emptiness stretching in every direction. Now, imagine you start to move, faster than any ship, faster than any planet, faster even than the starlight that has guided civilizations. You're on a voyage to the furthest conceivable point, the ultimate shore at the end of the cosmic sea. As you travel, the familiar constellations, the glittering islands of galaxies, begin to thin out. They become ghosts, their light red and weary from a journey of billions of years. Soon, they fade entirely. The universe of stars is gone. But you're not left in darkness. Instead, before you, in every direction, is a faint, luminous, shimmering wall. It glows with a serene, almost imperceptible warmth, a uniform curtain of light that encloses you completely. This is the edge. Not an edge of space, but the edge of time. You're staring at the first light ever to be free, a fossil from the moment the universe came out of its swaddling clothes of hot plasma and took its first clear breath. This is the cosmic microwave background, and it is the end of the road. The journey begins. To understand this wall, we first have to appreciate the journey. Our voyage doesn't start in the void, but right here, on a small, blue world orbiting an unremarkable star in a quiet spiral arm of the Milky Way. This is our "You are here" marker on the cosmic map. From our vantage point, the universe appears as a tapestry of stars, a view that has captivated humanity for millennia. But this view is just the first step on a staircase of incredible scale. Let's begin our journey outward. We pull away from Earth, watching oceans and continents shrink into a marbled sphere. The moon whips past in just over a second at the speed of light. Our sun, the anchor of our solar system, dwindles to a bright star. And here's a key idea to hold onto. Light doesn't travel instantly. Every ray of light is a messenger from the past. The light from our sun takes over 8 minutes to reach Earth. So, the further we look, the deeper back in time we see. Astronomers call this look-back time. We accelerate, our speed now measured in light years per second. The Oort cloud, the ghostly shell of icy bodies marking the edge of our solar system, flashes past. We're in interstellar space now. The stars around us, once fixed points, begin to shift and swirl, revealing their true three-dimensional arrangement. We're moving through the 100 billion stars of our home galaxy, the Milky Way. It's a staggering spiral disk, 100,000 light-years across. Crossing it, even at light speed, would take 100,000 years. But we press on. The Milky Way shrinks behind us, its beautiful arms blending into a single lens of light. It joins the Andromeda Galaxy and dozens of smaller galaxies to form the local group, our galactic neighborhood. And here, we can pause and look back. The light we see from Andromeda, our closest major galactic neighbor, left its source 2.5 million years ago. We're seeing Andromeda not as it is today, but as it was when early human ancestors walked the Earth. Every step of this journey is a step into the deep past. Our journey is far from over. We accelerate again, leaving the local group behind. Now, we see the true structure of the universe on its grandest scale. It isn't a random scattering of galaxies. It's a magnificent, intricate network of filaments and voids, a cosmic web. Galaxies are strung along colossal filaments of dark matter like pearls on a string, surrounding vast, empty voids that can span hundreds of millions of light years. Our local group is just one small part of the Virgo supercluster, which itself is just a lobe of an even grander structure called Laniakea. We are now billions of light years from home. The galaxies around us look different, smaller, bluer, more chaotic. We're seeing them in their youth. The light from these galaxies has been traveling for 5, 7, 10 billion years. We are seeing the cosmos as it was before our Sun, before our Earth, had even formed. The journey continues, pushing further into the void, deeper into time. Galaxies become sparser, their light fainter and more stretched. And it's here that the star-filled sky we've always known begins to disappear. The journey outward has reached a turning point. We're approaching the era before stars, before galaxies, before structure as we know it. We're approaching the end of the line. The fading of the stars. As we drift in this impossibly remote place, a profound question arises. Why did the stars fade? Why can't we see forever? This very question is known as Olber's paradox. If the universe were infinite, static, and eternal, then any line of sight should eventually hit a star. The entire night sky should be as bright as the sun. The fact that our night sky is dark is a clue of monumental importance. It tells us something fundamental about our universe. The answer comes in two parts, and they're both mind-bending. The first part is time. Our universe isn't eternal. It had a beginning about 13.8 billion years ago. This means light has only had 13.8 billion years to travel. We can only see objects whose light has had enough time to reach us. Light from a star 20 billion light years away simply hasn't arrived yet. This creates a horizon, a boundary in time. This is look-back time taken to its extreme. The second part is the expansion of the universe. In the 1920s, astronomers like Edwin Hubble discovered that light from distant galaxies was consistently shifted toward the red end of the spectrum. This, redshift, is a cosmic Doppler effect. Hubble found a stunning correlation. The farther away a galaxy is, the faster it's moving away from us. This was the first proof that our universe isn't static, it's expanding. But here's the crucial part. The galaxies aren't flying through space like shrapnel. The very fabric of space itself is stretching. A classic analogy is baking raisin bread. As the dough rises, all the raisins move farther apart. From any one raisin's perspective, all other raisins appear to be moving away, and the farther ones recede faster because there's more expanding dough between them. This expansion has a profound effect on light. As a photon journeys across billions of years of expanding space, its wavelength gets stretched along with it. This is called cosmological redshift. The brilliant, hot, blue light from a distant star can be stretched so much that by the time it reaches us, its energy is diluted, shifted through the visible spectrum into infrared, and even into microwaves. So, as we travel further out, we're looking at galaxies whose light has been traveling for billions of years, all while the universe has been stretching that light, draining it of its energy. This is why the stars fade. We're looking so far back in time that the light from these primordial galaxies has been redshifted into oblivion. Eventually, we reach a point in our look-back time before any stars or galaxies had even formed. For a period, the universe went through what astronomers call the cosmic dark ages. After the Big Bang's initial fires cooled, but before the first stars ignited, the universe was filled with a vast, dark gas of hydrogen and helium. There were no sources of light. So, there would be nothing to see from this era. We're peering back into a time of universal darkness. But this darkness wasn't the beginning. Before the Dark Ages, there was light. A brilliant, all-encompassing light. The reason we can't see past a certain point is not because of darkness, but because the early universe itself was an opaque, glowing, impenetrable fog. And the shimmering wall we've reached is the edge of that fog. The shimmering wall. Here we are, at the final frontier of our vision, gazing at this luminous wall that fills the entire sky. This is the cosmic microwave background, or the CMB. It is, without exaggeration, the most important relic in all of cosmology. To understand it, we have to rewind the clock all the way back. According to the Big Bang model, the universe began in an extraordinarily hot, dense state. For the first 380,000 years, it was still thousands of degrees a roiling, opaque plasma of atomic nuclei and free, unattached electrons. It was like being inside a dense, glowing fog. A photon of light couldn't travel far before slamming into a free electron and scattering in a random direction. Light was trapped. Then, something remarkable happened. After about 380,000 years, the universe cooled to a critical threshold of about 3,000 Kelvin. At this temperature, protons and nuclei could finally capture the free electrons, binding them into stable, neutral atoms. This event is called recombination. The moment recombination happened, the universe was transformed. With the free electrons locked away, the primary obstacle for light was gone. The dense, glowing fog suddenly cleared. The universe became transparent. Photons that were present at that exact moment were now free to travel in a straight line, unimpeded, across the cosmos. The shimmering wall we see is made of that very light. It's a snapshot of the universe at the precise moment it became transparent, the surface of last scattering. Imagine looking at the surface of a cloud. You can see the bright surface where light last scattered off water droplets, but you can't see inside the cloud. The CMB is the same idea, but for the entire cosmos. In every direction, we're seeing light that has traveled for nearly 13.8 billion years to reach us today. But why is it a microwave background? When this light was first released, it was brilliant and hot, with a temperature of 3,000 K, filling the sky with a bright, yellowish-orange glow. But in the 13.8 billion years since, the universe has expanded dramatically. This expansion stretched the wavelength of that light by a factor of about 100. Its brilliant visible light was shifted all the way down to the microwave portion of the spectrum. The faint energy we detect today corresponds to a temperature of just 725 degrees above absolute zero. So, the wall isn't a physical barrier. It's a temporal one, an image of the past. Its accidental discovery in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate a persistent hiss in their radio telescope, was one of the most important scientific discoveries of the 20th century. It was the definitive proof of the Big Bang, the echo of creation. What we see in the wall. At first glance, the cosmic microwave background appears astonishingly uniform. No matter where we look, we measure the same temperature. 725 Kelvin. This tells us the early universe was incredibly smooth. But when we look closer with sensitive instruments like the Planck Space Telescope, a breathtaking picture emerges. The wall isn't perfectly smooth. It's modeled with tiny variations in temperature fluctuations of just 1 part in 100,000. These are the CMB anisotropies, and they are the seeds of everything we see in the universe today. The slightly warmer, redder patches represent regions that were infinitesimally denser than average. The slightly cooler, bluer patches were infinitesimally less dense. What caused these tiny wrinkles? The leading theory, cosmic inflation, proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion. During this stretching, tiny quantum fluctuations were magnified to astronomical proportions. The CMB map is, in a very real sense, a photograph of quantum mechanics playing out on a cosmic scale. After inflation, these density variations began to evolve. The denser regions had slightly more gravity, which pulled matter in, while the intense pressure of trapped photons pushed back out. This created sound waves, acoustic oscillations that sloshed through the primordial plasma. The CMB is a snapshot of these sound waves at the exact moment the universe became transparent. The size of the hot and cold spots corresponds to the wavelengths of these ancient sound waves. Analyzing these fluctuations has become the bedrock of modern cosmology. It allows us to measure the fundamental parameters of our universe with astonishing accuracy. For example, the most common size of the spots in the map acts as a cosmic ruler. By measuring how large they appear to us, we can determine the geometry of spacetime, which the data shows as flat on large scales. By analyzing the CMB's power spectrum, a graph showing the amount of variation at different sizes, scientists can also determine the exact recipe of the cosmos. The data tells us our universe is made of about 5% ordinary matter, the stuff of stars, planets, and 27% dark matter, an invisible substance holding galaxies together, and a staggering 68% dark energy, a mysterious pressure accelerating the universe's expansion. These tiny fluctuations are the direct ancestors of all the structure we see today. Over hundreds of millions of years, gravity sculpted these seeds into the first stars and galaxies, which then formed the great cosmic web. Every galaxy, every star, every planet can trace its origin back to one of these tiny, random fluctuations. We are, quite literally, the descendants of the patterns on this shimmering wall. The true edge of knowledge. We've reached the wall. We've seen what it is and what its patterns mean. But now we have to confront the most profound part of this journey. We know the universe is about 13.8 billion years old. So, it seems logical that this wall of light is 13.8 billion light years away. But this is wrong. The place that emitted the light we see today as the CMB is now approximately 46 billion light years away. This gives the observable universe a diameter of about 92 billion light years. How is this possible? How can something be 46 billion light years away if nothing can travel faster than light? The key, once again, is the expansion of space. Nothing with mass can travel through space faster than light. That rule is unbroken. But the rule doesn't apply to the expansion of space itself. Space can, and does, expand faster than the speed of light. Think of our photon, emitted 380,000 years after the Big Bang. At that moment, the region of plasma that released it was much closer to what would become the Milky Way, only about 42 million light years away from us in today's terms. But as the photon began its journey, the space between it and its destination was constantly stretching. It's like a traveler on an expanding road. They walk at a constant speed, but the road itself is being stretched out in front of them. Their journey becomes much longer than their walking speed would suggest. Our photon traveled a path of 13.8 billion light years, but the starting point of that path was carried away from us by cosmic expansion to its current, staggering distance of 46 billion light years. This boundary is called the asterisk particle horizon. It's a sphere centered on us, and its edge represents the maximum distance from which light could have traveled to reach us today. This shimmering wall, the surface of last scattering, is effectively draped over the inside of our particle horizon. It's the furthest and oldest thing we can possibly see with light. It's also important not to confuse the particle horizon with the asterisk event horizon. The particle horizon is a boundary in the past, the edge of what we can see now. The event horizon is a boundary in the future. Because expansion is accelerating, there are galaxies we can see today whose light is fighting a losing battle. Beyond a certain distance, currently about 16 billion light-years, any light a galaxy emits now * will never reach us. Space is expanding too fast. Those galaxies are being pulled beyond our cosmic event horizon, and they will eventually fade from our sky, forever. But the particle horizon, the CMB wall, is the true edge of our knowledge of the past. It isn't a physical wall you could touch. If you could magically travel to that location 46 billion light-years away, the wall wouldn't be there. You'd find yourself in a galaxy much like our own, at the center of your own, new observable universe. And you'd look out and see a shimmering wall of microwave light 46 billion light-years away in the direction of Earth. The horizon moves with the observer. It's a boundary of information, telling us, this is as far as you can see. Our journey is complete. We've traveled from our home on Earth, past the stars and galaxies, to the furthest reaches of space and time. We've arrived at the end of the line, not at a barrier of matter, but at a boundary of light. Here, at the edge of everything we can know, we're surrounded by a soft, shimmering wall, the faint, cold echo of our universe's fiery birth. This wall, the cosmic microwave background, is more than just ancient light. It's a cosmic Rosetta Stone. Its faint glow tells the story of our universe's age, its shape, and what it's made of. The tiny fluctuations dappled across its surface are the ancestral seeds from which all galaxies, all stars, and ultimately, we ourselves, have grown. We've learned this wall is now a staggering 46 billion light-years distant, a testament to the awesome power of expanding space. It defines the boundary of our observable history, a bubble of knowledge in an ocean of the unknown. Beyond it, the universe likely stretches on, perhaps infinitely, filled with wonders we will never see. To stare at this wall is to be humbled, but it's also a source of profound connection. That light, released when the universe was an infant, has traveled across the entire expanse of cosmic history to fall upon our telescopes. It crossed billions of light-years of expanding, darkening space to bring us a message from our own origin. The shimmering wall at the end of space-time isn't an end, but a beginning. It's the beginning of light, the beginning of structure, and the beginning of our quest to understand it all. And it leaves us with the most wondrous thought of all. We are here, now, able to witness the echo of our own creation. If this journey to the edge of time sparked your curiosity, consider subscribing for more explorations into the cosmos. Our universe is filled with wonders, from the mysteries of black holes to the search for life beyond Earth, and we have many more journeys to take together. You can also support the creation of these videos on Patreon, allowing us to dive even deeper into the science that shapes our understanding of everything. And if you're not ready for the journey to end, you can click here to watch our next video on what might lie beyond the horizon itself. Space is expanding faster than light, and it's terrifying. When you look up at the night sky, it feels like you're staring into an infinite sea of possibilities. Billions of stars and countless galaxies, all just waiting to be explored. It's a canvas of unending potential, a promise of discoveries yet to come. But what if I told you that most of what you're seeing is already out of reach? That there are entire galaxies, home to trillions of stars and who knows how many worlds, that we are already cut off from forever. We can see their ancient light, a ghost from a time long past, but we can never, ever reach them. Because the very fabric of space is carrying them away from us faster than light. This isn't science fiction. This is the unnerving reality of our cosmos, and it forces us to confront the profound, inescapable loneliness of our place in the universe. The Great Revelation. For most of human history, we thought the universe was a pretty comfortable place. It was the heavens, a fixed and eternal sphere of stars. This wasn't just an ancient idea, even the giants of science believed it. In the early 20th century, Albert Einstein himself was convinced the universe was static. When he finished his game-changing theory of general relativity in 1915, his own equations told him that a universe full of matter should be collapsing under its own gravity. That didn't feel right to him, so he added a little fudge factor, a mathematical patch he called the cosmological constant. Its only job was to push back against gravity and keep the universe perfectly still. But the universe, as it turns out, isn't a tidy, balanced system. The first clue came from an American astronomer named Vesto Slipher. In the 1910s, he spent year after year at the Lowell Observatory, carefully analyzing the light from what they called spiral nebulae. Using a technique called spectroscopy, which splits light into a rainbow of colors, he found something baffling. The light from nearly all of these nebulae was shifted towards the red end of the spectrum. This redshift is a cosmic version of the Doppler effect. Think of a siren. As it races toward you, the pitch is high. As it speeds away, the pitch drops. Light does the same thing. Light from something moving away gets stretched into longer, redder wavelengths. Slipher's observations showed that almost every nebula he looked at was racing away from us at incredible speeds. It was the first real piece of evidence that the universe wasn't static at all. Slipher knew what was happening, but not why. The next piece of the puzzle came from Henrietta Swan Leavitt, a human computer, at Harvard Observatory. She discovered a critical trick using a special type of star called a Cepheid variable. These stars pulse, and Leavitt found that the speed of their pulse is directly linked to their true brightness. This meant they could be used as standard candles. By comparing how bright a Cepheid star looked from Earth to how bright it actually was, astronomers could finally calculate its distance. This was the key. In the 1920s, astronomer Edwin Hubble, using the massive Hooker telescope at Mount Wilson, started hunting for these Cepheids in the spiral nebulae. He found them, and his calculations were mind-blowing. These nebulae weren't gas clouds in our own galaxy. They were millions of light-years away vast, separate galaxies, or island universes. For the first time, humanity began to grasp the true scale of the cosmos. But Hubble didn't stop there. He put his distance measurements together with Slipher's redshift data. When he plotted them on a graph, the pattern was shockingly clear. The farther away a galaxy was, the faster it was moving away from us. This became known as Hubble's law, and it was the final nail in the coffin for a static universe. The universe was expanding. When Einstein heard about Hubble's findings, he visited him at Mount Wilson to thank him, famously calling his cosmological constant his greatest blunder. The comfortable cosmos was dead. In its place was a universe born from a violent beginning, expanding ever outward. But no one, not even Hubble or Einstein, could have guessed the most terrifying part of this story: the stretching of space-time. To get why this is so terrifying, we have to get the physics right. Because this expansion isn't what it sounds like. Our intuition pictures galaxies flying through space like shrapnel from some central explosion. But that's not what's happening. This is the first mind-bending idea you have to accept. The galaxies aren't moving through space. It's space itself that's expanding, carrying the galaxies along for the ride. The classic analogy is to imagine drawing dots on a balloon. Each dot is a galaxy. As you inflate the balloon, the rubber stretches, and every dot moves away from every other dot. From any one dot, it looks like all the others are rushing away. The farther away a dot is, the faster it recedes, because there's more stretching rubber between them. That's our universe. This is what physicists call cosmological redshift, the stretching of light waves as the space they travel through expands. This is a critical distinction because of Einstein's ultimate speed limit. Nothing can travel through space faster than the speed of light. So how can distant galaxies be moving away from us faster than light? The answer is they aren't moving through space at all. The speed limit applies to motion within the fabric of spacetime. The expansion of spacetime itself has no speed limit. There's no law of physics that stops 2 points in space from separating at faster than light speeds, because nothing is actually traveling between them. The space is simply growing. This isn't a violation of relativity, it's a consequence of it. For decades, cosmologists figured the gravity from all the stuff in the universe would eventually slow this expansion down, maybe even reverse it in a big crunch. Then came 1998. Two teams of astronomers were using distant supernovae to measure the expansion rate in the past. They expected to see it slowing down. They found the exact opposite. The expansion of the universe was speeding up. The discovery was so shocking it won a Nobel Prize. Something was pushing space apart, overpowering gravity. Scientists didn't know what it was, so they gave it an appropriately mysterious name: dark energy. We still don't really know what dark energy is, but it makes up about 68% of everything in the universe. The leading idea is that it's a property of space itself. As space expands, more space gets created, and with it, more dark energy, which pushes space to expand even faster. It's a runaway feedback loop. This acceleration began to dominate over gravity's braking effect roughly 5 to 6 billion years ago. And this acceleration is the engine of our cosmic isolation. The three horizons of the apocalypse. You know what a horizon is on Earth. It's the farthest you can see before the planet curves away. In cosmology, horizons are far more absolute. They aren't just limits on what we can see, but fundamental limits on what we can ever interact with. To understand our cosmic prison, you have to understand its walls. The particle horizon, the Hubble sphere, and the most frightening of all, the cosmic event horizon. First, the asterisk particle horizon. This is the edge of the observable universe. The universe is about 13.8 billion years old, so you might think we can see 13.8 billion light years in every direction. But you'd be wrong. As light travels toward us from a distant galaxy, the space it's moving through is stretching. It's like trying to run up a downward moving escalator. Because of this, the galaxy that emitted the light is now much farther away. When you do the math, the edge of our observable universe, the particle horizon, is currently about 46.5 billion light years away. Everything inside this 93 billion light year wide sphere is what we can, in principle, see. Next up is the asterisk Hubble sphere. This is a more direct concept. Remember Hubble's law? The farther away a galaxy is, the faster it recedes. The Hubble sphere is the distance where that recession speed hits the speed of light. Right now, that boundary is about 14.4 billion light years away. Every galaxy beyond the Hubble sphere is, at this very moment, receding from us faster than the speed of light. Let that sink in. There are galaxies we can see right now with the Webb telescope whose light is just reaching us, but the galaxies themselves are already moving away faster than light. We are watching their past, but their present is superluminal. This brings us to the final, most terrifying wall. The asterisk cosmic event horizon. This is the true boundary of our inescapable prison. The cosmic event horizon is the ultimate point of no return. It's the largest distance from which light emitted right now can ever reach us. Because of the accelerating expansion, this boundary is currently a bit farther out than the Hubble sphere, at an estimated distance of about 16 billion light years. Here's the chilling logic. Imagine a galaxy 17 billion light-years away. It's outside our event horizon. It sends out a photon today, aimed right at us. But the space between us and that galaxy is expanding so fast that the photon is like a swimmer caught in a current that's too strong. It gets swept away. It will never, ever reach Earth. That galaxy, and every galaxy beyond the 16 billion light-year event horizon, is causally disconnected from us. Forever. The terrifying revelation. Let's put the pieces together to see the full, terrifying picture. We sit at the center of our observable universe, a sphere about 93 billion light-years across. Inside this bubble, based on our best estimates, lies somewhere around 2 trillion galaxies. An almost unimaginable number. But that's just the light from the past. Let's talk about the future. The cosmic event horizon is the line in the sand. Any galaxy in our observable universe that is already beyond that 16 billion light-year line is lost to us. According to cosmological models, this amounts to a staggering 94% of all the galaxies we can currently detect. Let that sink in. Of the 2 trillion galaxies we can theoretically see, we will only ever be able to interact with or travel to about 6% of them. The other 94%? They're cosmic ghosts. We can see their baby pictures, the ancient light they sent out billions of years ago. But in our present, they have already been swept beyond the point of no return. Think of one of the most distant galaxies confirmed by the James Webb Space Telescope, an object like MOM Z14. We are seeing light it emitted just 280 million years after the Big Bang, a snapshot from the cosmic dawn. But in the 13.5 billion years it took that light to reach us, cosmic expansion has carried that galaxy far, far away. It is now well beyond our cosmic event horizon. We can study its past, but we can never visit it, never communicate with it, and never know what it's doing right now. It is gone. And so are trillions of others. And it gets worse. Because of dark energy, the expansion is accelerating. This means that, over time, more and more galaxies will be carried across the event horizon. We will witness, in excruciatingly slow motion, as entire galaxies appear to freeze, their light stretching into nothingness, as they vanish from our future. Billions of years from now, the night sky for our descendants will be a profoundly emptier, darker place. Almost every galaxy beyond our own local group will have been swept away by the tide of expanding space, their light redshifted into oblivion. This is the true terror. We're living on a shrinking island in a vast cosmic ocean. The shores of this island are the event horizon, and the tide of dark energy is relentlessly pulling the rest of the universe away. There is no starship or warp drive that can overcome this, because you can't outrun the expansion of space itself. We are, in a very real sense, alone. The philosophical aftermath. So, what does it mean to live in a universe like this? It's easy to feel a profound sense of cosmic loneliness. The fact that 94% of the galaxies we can see are already unreachable ghosts makes our little corner of the cosmos feel like a tiny, marooned archipelago. Does this make us insignificant? In a way, yes. It highlights a universe so vast we can never even know its full extent. But there's another way to look at it. Maybe this isolation makes everything we can see infinitely more precious. We are living in a very special, privileged moment in cosmic history. We exist in the era after the Great Acceleration has begun, but before it has had time to erase everything from our sky. We can still see the afterglow of the Big Bang. We can still see those impossibly distant, infant galaxies with our telescopes. We are alive in the sliver of cosmic time where it's possible to piece together the entire story of the universe. Future civilizations, billions of years from now, might not have that luxury. They might inherit a sky that appears static and empty, with no clues to its explosive origin. They might never know the true story. This gives our scientific mission a sense of urgency. We are the universe's historians, capturing the last light from a cosmos that is slowly dismantling itself from our view. It also reframes what exploration means. If we can't travel there, our telescopes become our only starships. Each photon the Webb telescope collects from a galaxy beyond the event horizon is a message from a lost world, a piece of a story that has crossed an impossible gulf to reach us. The Hubble tension. The ongoing debate over why our measurements of the universe's expansion rate don't line up adds another layer here. Measurements of the early universe suggest an expansion of about 67 kilometers per second, MPC, while measurements of the local, modern universe give a faster rate of around 73 kilometers per second, MPC. Recent data from JWST have confirmed that this isn't just a measurement error, suggesting there might be new physics we don't understand yet. It's a humbling reminder that even the walls of our cosmic prison hold secrets we're still trying to figure out. The universe is constantly challenging us with mysteries that are as terrifying as they are awe-inspiring. If you want to keep exploring these profound questions about our cosmos, from the nature of dark energy to the fate of reality itself, make sure to subscribe and join us on this journey into the unknown. A fleeting glimpse of infinity. The idea that space is pulling itself apart faster than light, cutting us off from almost everything, is a tough pill to swallow. It's a confrontation with the ultimate limit, a cosmic loneliness that feels absolute. But inside that terrifying thought is a sense of profound wonder. We are the generation that gets to see it all. We are living in the twilight of the visible universe, a fleeting moment where the view is still magnificent, where the story of our origins is still written across the sky. The ancient light from galaxies we can never touch still reaches us, telling the story of what once was. The coming darkness gives the light we see now an almost sacred value. It reminds us that our view of the cosmos is a privilege of time and place. So, the next time you look up at the night sky, don't just see an infinite sea of possibilities. See a beautiful, fleeting, and impossible collection of cosmic ghosts. See the last light from a universe that is slipping through our fingers, and be grateful you are here to witness it, before it all fades to black. What science just discovered beyond the universe's edge? For as long as we've been human, we've looked up at the night sky and asked a simple question. Where does it all end? It's the oldest question there is. We're standing on this tiny island of rock and water, staring out into a black ocean dotted with pinpricks of light. We've mapped our solar system, our galaxy, and we've used our telescopes to catch the light of galaxies billions of light years away. But the question is always there. What happens when you get to the end? Is there a wall? Some final barrier? What's on the other side? What if I told you that you, right now, are at the very center of everything we can see, but you're also trapped inside a bubble made of light? What if the edge you're looking for isn't a place, but a time? For centuries, we've been staring at the answer, and it's just now starting to become clear. We are on the verge of understanding what's beyond that boundary, and the truth is wilder, more complex, and more profound than we ever dreamed. This is the story of the cosmic horizon, a shimmering veil that hides a reality that might just be infinite. This is the story of what science is discovering beyond the edge of our universe. The illusion of an edge, your personal universe. To start this journey, let's forget about space for a second. Picture yourself on a quiet beach at dusk. The waves are lapping at the shore, and you're looking out at the ocean. Far in the distance, you see that perfectly straight line where the dark water meets the sky. That's the horizon. You know, instinctively, that it's not a real edge. It's not a cosmic waterfall where the ocean just pours into nothing. If you got in a boat and sailed for it, the horizon would just move with you. It's a limit of your perspective, a line drawn by the curve of the Earth and your spot on it. Now, let's blow that idea up to the biggest scale imaginable. The universe works a lot like that. The edge we talk about in cosmology isn't a physical wall, but a horizon of light. It's called the asterisk particle horizon asterisk, and it defines the boundary of the asterisk observable universe. And just like on that beach, you are at the dead center of it. This isn't because Earth is special. It's because light travels at a finite speed, the ultimate speed limit of the cosmos. The universe, according to our best measurements from missions like the Planck satellite, is about 13.8 billion years old. This means the absolute farthest we can possibly see is the distance light has had time to travel in 13.8 billion years. Any light from any object farther away than that is still on its way. Those ancient photons just haven't had enough time to reach our telescopes. This creates a perfect sphere of observation around us, with Earth right in the middle. But here's where it gets a little weird. That sphere isn't 13.8 billion light years in radius. The actual radius is a mind-boggling 46.5 billion light years. That makes the total diameter of everything we can see about 93 billion light years across. So, how can the universe be so much bigger than its age in light years? This paradox is solved by one of the greatest discoveries of the 20th century. The universe is expanding. Space itself is stretching. The classic analogy is a loaf of raisin bread baking in an oven. As the dough rises, all the raisins move away from each other. From the perspective of any one raisin, all the others seem to be rushing away. The farther away another raisin is, the faster it seems to move, because there's more expanding dough between them. In this picture, the raisins are galaxies, and the dough is the fabric of space-time. Our Milky Way is just one of those raisins. We aren't expanding into some empty void. The actual space between galaxies is expanding, carrying them along for the ride. Now think about that light from a distant galaxy, which started its journey to us 13.8 billion years ago. While it was racing toward us at the speed of light, the space it was traveling through was constantly stretching. So, by the time that ancient light finally gets to us, the galaxy that sent it is now much, much farther away, a distance calculated to be around 46.5 billion light years. This is how we end up with our gigantic observable bubble. This stretching of space also stretches the light itself. As photons travel across billions of years of expanding space, their wavelengths get longer, shifting them toward the red end of the spectrum. This is what astronomers call redshift, and it's the universe's own cosmic speedometer. The farther a galaxy is, the more its light is redshifted, and the faster it appears to be moving away. So, just like on the beach, our view is limited by a horizon. But our cosmic horizon isn't set by the curve of the Earth. It's set by the age of the universe and the finite speed of light. Every single observer in the cosmos, in any galaxy, is at the center of their own unique observable universe, with their own personal particle horizon. An alien astronomer a billion light years away would see their own 93 billion light-year sphere, with their planet at the center. They'd see parts of the cosmos that are beyond our horizon, and parts of our universe would be invisible to them. There's no center of the universe, only the center of your own bubble of light. The echo of creation. The ultimate wall of light. If we could look all the way to the edge of what we can observe, what would we see? You might expect to see the very first baby galaxies flickering on. But we don't. Instead, when our most sensitive radio telescopes look in any direction, they see something else. A faint, persistent, nearly uniform glow of microwave radiation. It isn't coming from a star or a galaxy. It's coming from the edge of observable time itself. This is the asterisk cosmic microwave background asterisk, or CMB. The CMB is often called the afterglow of the Big Bang, and it's the single most important piece of evidence we have for how our universe began. It is, literally, the oldest light we can see, a fossil from a time when the entire cosmos was a completely different place. To understand it, we have to travel back to about 380,000 years after the Big Bang. In those early moments, the universe was an unimaginably hot, dense soup of plasma, a chaotic fog of fundamental particles and, most importantly, free-roaming electrons. Photons of light couldn't travel more than a few feet without being scattered by an electron. It was like being inside a star, or trying to see through an impossibly thick fog. The entire universe was opaque. For 380,000 years, the universe kept expanding and cooling. Finally, it hit a critical milestone. The temperature dropped to about 3,000 Kelvin. At that point, it was just cool enough for the free electrons to be captured by protons, forming the first stable atoms of hydrogen and helium. This event is called recombination. The moment recombination happened, the universe transformed. With the electrons now bound up in atoms, the cosmic fog suddenly cleared. The photons of light, which had been bouncing around like pinballs, were suddenly free to travel in a straight line. For the first time ever, the universe became transparent. The cosmic microwave background is the light from that very moment of last scattering. It's a baby picture of the universe when it was just 380,000 years old. As this ancient light has traveled for 13.8 billion years to reach us, the expansion of space has stretched its wavelength enormously. What started as the brilliant light of a 3,000 plasma has been redshifted all the way down into the cold, invisible microwave part of the spectrum, with an average temperature of just 2,725 degrees above absolute zero. Think of it like this. You're standing in the middle of a giant, hollow sphere. The inner surface of that sphere is the CMB. When you look out in any direction, your line of sight eventually ends at this surface of last scattering. You can't see what came before it, not because nothing was there, but because the universe itself was opaque. It's like looking at the surface of the sun. You can't see into the core because the surface is the point where light can finally escape. The CMB is the remnant of that cosmic surface that once filled all of space. When we map the CMB with incredible precision using probes like COBE, WMAP, and Planck, we find it isn't perfectly uniform. There are tiny temperature fluctuations, hot and cold spots that vary by only 1 part in 100,000. These almost invisible ripples were the seeds of everything we see today. The slightly denser, cooler spots had more gravity, and over billions of years, they pulled in matter, eventually collapsing to form the first stars, galaxies, and the vast cosmic web. We are, quite literally, the descendants of those tiny ripples in the afterglow of creation. The CMB is the ultimate boundary to our vision, a wall of light that we can never see past with any telescope. The great unknown. What lies beyond the light? So, we've journeyed to the absolute edge of what we can see, a wall of light from 380,000 years after the Big Bang. This brings us to the ultimate question. What's on the other side? What lies beyond the horizon of our observable universe? The simplest, and maybe the most profound, answer has been hiding in plain sight. More universe. There's no physical or theoretical reason to think the universe just stops at the edge of what we can see. Remember the ocean horizon. The world doesn't end where your vision does. The same idea almost certainly applies here. The region beyond our particle horizon isn't a void or another dimension, but just more of the same cosmos we live in. More stars, more galaxies, more clusters, stretching on and on. This idea is formalized in what scientists call the cosmological principle. It's a foundational assumption that says on the largest scales, the universe is homogeneous. it's roughly the same everywhere. And asterisk isotropic. It looks the same in every direction. Decades of mapping how trillions of galaxies are arranged in a vast cosmic web have shown this principle holds up remarkably well. Our corner of the universe doesn't seem to be special. If our location isn't special, it stands to reason the universe continues far beyond the 93 billion light-year sphere we can see. But how far? The answer might just be forever. Our most precise measurements of the CMB have allowed us to determine the overall geometry of space. It could be positively curved, like a sphere, which would make it finite but without an edge, or it could be negatively curved, like a saddle, which would be infinite, or it could be flat. Amazingly, data from the Planck satellite show the universe to be incredibly flat, with a margin of error of less than 1%. A flat universe is the simplest geometry, and its simplest implication is that it extends infinitely in all directions. If it is infinite, then our entire observable universe, all 93 billion light-years of it, is just one infinitesimal patch in a cosmos that goes on forever. This is where science tips into philosophy and leads to a stunning, if controversial, idea. The asterisk level 1 multiverse. This isn't a sci-fi theory about other dimensions. It's a direct logical consequence of an infinite universe. If the universe is infinite and contains a finite number of ways particles can be arranged, as quantum mechanics suggests, then any event with a non-zero probability has to happen an infinite number of times. Think about what that means. In our observable universe, particles can only be arranged in a huge, but finite, number of ways. If you travel far enough through an infinite cosmos, you'll eventually find another region of space where the initial conditions were so similar to ours that an identical Milky Way formed. Go even further, and you'll find a solar system with a planet just like Earth. And further still, there would be a perfect copy of you. And another copy who chose a different path in life. Every possible variation, every choice you could have made, is being played out somewhere across this infinite cosmic tapestry. These other universes are just so far away, so far beyond our particle horizon, that we could never, ever interact with them. The theory that provides a physical mechanism for such a vast, flat universe is asterisk cosmic inflation. It suggests that in the first tiny fraction of a second after the Big Bang, the universe went through a period of unbelievably rapid, exponential expansion. This hyper-expansion would have stretched space-time so much that it became effectively flat on the scales we can see, just like the Earth seems flat to us on the ground. Inflation blew up a tiny patch of the early universe to a scale vastly larger than our current horizon, making a near-infinite universe a natural outcome. The vanishing future. The cosmic event horizon. We've explored the horizon in our past, the cosmic microwave background, and the horizon that defines what we can see right now. But there's a third, more unsettling horizon. One that isn't defined by the past, but by our ultimate future. It's called the asterisk cosmic event horizon. To get a handle on this, we have to talk about the most mysterious force in physics: dark energy. In the late 1990s, astronomers studying distant supernovae found something shocking. The universe wasn't just expanding, the expansion was accelerating. It was as if you threw a ball in the air, and instead of slowing down, it started shooting upward, faster and faster. There had to be some kind of invisible energy built into the fabric of space itself, pushing everything apart. They named it dark energy, and it's thought to make up nearly 70% of the universe. This accelerating expansion creates a point of no return. As space stretches faster and faster, there's a distance at which galaxies are carried away from us faster than the speed of light. This doesn't violate Einstein's theory of relativity. The galaxies aren't moving through space that fast. Rather, the space between us and them is expanding so rapidly that it outpaces the speed of light. The cosmic event horizon is the boundary that marks this point. It's currently about 16 billion light-years away. Any galaxy that is already beyond this line is lost to us forever. The light it emits today, even as it races toward us, will never complete the journey. It's like trying to swim upstream in a river flowing faster than you can swim. The light from those galaxies is fighting a losing battle against the torrent of expanding space. This is a much more final boundary than the particle horizon. Our particle horizon grows as the universe gets older and light from farther away finally reaches us. But the event horizon is a closing door. Because of the accelerating expansion, galaxies we can see today will eventually cross this event horizon in the far future and vanish from our view. Their light will get more and more redshifted until it fades away completely. This leads to a pretty chilling prediction for the ultimate fate of the cosmos, at least under the Standard Model. A future of deep loneliness. Trillions of years from now, all the distant galaxies we see with our telescopes will be gone. They will have receded beyond our event horizon, their light stretched into nothing. The cosmic microwave background itself will have faded into undetectability. An astronomer in this far future would look out and see only the stars of their own galaxy, surrounded by an endless, featureless void. All the evidence of the Big Bang and a wider cosmos would be erased. This desolate end is often called the heat death of the universe. For decades, this cold, empty future seemed to be our destiny. The discovery, a new cosmic destiny? For decades, the story of the cosmos seemed to be a one-way trip toward isolation and darkness. But what if the engine driving that expansion isn't constant? What if there's a plot twist hiding in the data? In the last few years, a series of stunning results from our most powerful cosmological surveys have started to hint at something that could rewrite the final chapter of the universe. This new chapter comes from projects like the Dark Energy Survey, DE*, and the Dark Energy Spectroscopic Instrument, DESI. DESI is an incredible instrument mounted on a telescope in Arizona, and it has 5,000 robotic fiber optic eyes that can measure the light from thousands of galaxies at once. These surveys are building the largest 3D maps of the universe ever created, tracing the history of cosmic expansion over the past 11 billion years with stunning accuracy. The long-held theory of dark energy was that it's a cosmological constant an unchanging property of space itself. If that's true, the fate of a cold, empty heat death is sealed. But new data from DESI and DE, when combined with other cosmological measurements, are showing tantalizing hints that this might not be the full story. The results suggest dark energy might actually be dynamic, that its influence is changing over time. This alternative idea is known as quintessence. Unlike a constant, quintessence is a dynamic field that can change its strength. The latest results are strengthening the evidence that dark energy's influence may be weakening over time. While this doesn't yet meet the 5 sigma gold standard for a discovery, different analyses show a preference for evolving dark energy at a level between 2, 8 and 4. 2 sigma, meaning it's still possible it's a statistical fluke, but it's getting harder to ignore. If dark energy is indeed evolving, some scientists are exploring a shocking possibility. What if the expansion doesn't just slow down, but stops and reverses entirely? If the repulsive force of dark energy weakens enough, gravity could once again become the dominant force on a cosmic scale. The universe would stop expanding and begin to contract. This would lead to a fate not of cold emptiness, but of incredible fire. A big crunch. Instead of receding, galaxies would start rushing toward each other. The sky would fill with the blue shifted light of approaching galaxies. Over billions of years, the universe would get smaller, hotter, and denser, ending in a cataclysmic collapse, a Big Bang in reverse. Some models, based on these new hints, place this reversal about 20 billion years in our future. This would mean the cosmic event horizon is just a temporary illusion. As the universe contracts, we would start to receive light from galaxies that are currently beyond that horizon, expanding our view of the cosmos. It's absolutely critical to be clear. This is cutting-edge science, and these hints are far from definitive proof. The standard model of cosmology, which predicts eternal expansion, still fits the data well. However, these anomalies are forcing cosmologists to consider that our current model might need an update, opening the door to a new and uncertain cosmic fate. The discovery that the universe's expansion was accelerating was a Nobel Prize-winning revelation. Finding out that it might be slowing down and reversing would be just as profound. The story of the cosmos is constantly being rewritten, with new chapters added by discoveries just like this. We are living in a golden age of cosmology, where our instruments are finally powerful enough to challenge our deepest assumptions about reality. The universe is far stranger and more wonderful than we can imagine, and its greatest secrets are still waiting to be uncovered. If you want to stay on the front lines of discovery, then be sure to subscribe and click the notification bell. We're all on this journey together, and we're just getting started. We started with a simple question. What's beyond the edge? Our journey took us from a familiar ocean horizon to the very limits of light and time. We've seen that you are at the center of your own cosmic bubble, a bubble defined not by a wall, but by the finite speed of light. We've peered back to the afterglow of the Big Bang, a shimmering veil we can't see beyond. Beyond that veil, we've wrestled with the mind-bending possibility of an infinite cosmos. And now, on the cutting edge of science, we've found hints that our universe's destiny might not be a cold, lonely end, but a spectacular, fiery collapse. What does it mean to live in a universe that might not end with a whimper, but with a bang? The only thing we know for sure is that for every question we answer, the cosmos gives us a dozen more, each more profound than the last. The greatest discoveries are still to come. Why you can never fall off the universe. What if I told you that you could travel in a straight line, forever, and not only never reach an edge, but actually end up right back where you started? It sounds like a riddle, a total contradiction. How can something have a limited size, but no boundary? Well, this isn't a riddle. It's the wonderfully weird reality of the cosmos we live in. For as long as we've looked up at the stars, we've pictured the universe as a giant, dark room, with all the galaxies sprinkled inside. We think of it expanding, like a bubble getting bigger and pushing into some empty blackness. But what if there is no beyond? What if the very idea of an edge of the universe is a total misunderstanding of what the universe even is? Today, we're going on a trip to the very limits of what we know, to see why you can never, ever fall off the universe. We're going to have to tear down our mental picture of the cosmos and replace it with something far stranger, and we'll do it with one of the most famous analogies in all of science. So, stick around, because reality is about to get weird. The problem of the edge. When you try to picture the universe, what do you see? For most of us, it's an image we all share. We see a sphere, or maybe a bubble. Inside are all the galaxies, stars, and planets. And we know this bubble is getting bigger. That's the expansion of the universe. But what's it expanding into? An endless, black void? Nothingness? This is the image we see in movies and in our own heads. It just feels right. An expanding thing has to expand into something else. It has to have a border separating the inside from the outside. This is exactly where our intuition, built from a lifetime of dealing with everyday objects, completely fails us. When cosmologists talk about the universe expanding, they don't mean it's a bubble blowing up in a pre-existing, empty room. The universe is the room. The expansion is happening to space itself. The very fabric of reality is stretching. There's no outside for it to expand into because, by definition, the universe is everything. Asking what the universe is expanding into is like asking what's north of the North Pole. The question itself doesn't make sense. This can break your brain a little, so let's ground it. A lot of the confusion comes from mixing up two very different things: the observable universe and the asterisk entire universe. They are not the same. The observable universe is the part of the cosmos that we can see from Earth. It's a sphere of visibility with a smack dab in the middle. But why a sphere? Why is there a limit? It's not a wall. It's a horizon made of time and light. The universe is about 13.8 billion years old. That means light has only had 13.8 billion years to travel through space to get to us. So when we look out, we can only see things whose light has had enough time to complete the journey. Anything farther away is still out there, but its light just hasn't reached us yet. This creates a cosmic horizon. Think of it like the horizon at sea. Standing on a beach, you can only see so far before the Earth's curve hides the rest of the ocean. You know there's more ocean past that horizon. You just can't see it from where you are. The cosmic horizon is the same deal, but with light and time instead of Earth's curve. So, we sit at the center of our observable universe, a bubble about 93 billion light-years across. But here's the key. An alien in a galaxy 10 billion light-years away would be at the center of its own observable universe. Neither of us is special. Every point in the cosmos is the center of its own little bubble of sight. So, the only edge we can talk about for sure is just the edge of what we can see, not the edge of what exists. The real question, the much deeper and weirder question, is about the shape and size of the asterisk entire universe. Does that have an edge? To answer that, we need to leave our intuition at the door and embrace a classic analogy. The balloon analogy. Our guide to the cosmos. To really get a feel for the strange shape of our cosmos, let's try a little thought experiment. Forget for a minute that we live in 3 dimensions. I want you to imagine you're a perfectly flat, 2-dimensional creature. Your whole world exists on a surface, like a drawing on a piece of paper. Now, imagine you live on the surface of a balloon. Let's grab a balloon and a marker. We'll draw dots all over it, each dot representing a galaxy. You, our 2D explorer, live on one of these dots. Now, we start blowing up the balloon. As the rubber stretches, something amazing happens. From your dot, every other dot starts moving away from you. The ones nearby move away slowly. The ones farther away move away much faster. This is a perfect match for what Edwin Hubble saw in the 1920s. The farther a galaxy is, the faster it's speeding away from us. It's the classic sign of space expanding uniformly. But here's the twist. Are you at the center of the expansion? Nope. If you jump to any other dot, you'll see the exact same thing. All the other dots are moving away from you. On the 2D surface of the balloon, there is no center. The expansion is happening everywhere at once. The actual center of the balloon, the point in the 3D space inside, isn't part of your 2D universe. The surface is all there is. This is why the Big Bang wasn't an explosion in space, but an expansion of space. It happened everywhere, all at once. Now for the most important part. As our 2D friend on the balloon, start walking in a straight line. Pick a direction and just go. What happens? You walk and walk, past galaxy after galaxy. You never hit a wall. You never find a cliff where the balloon just stops. You never fall off. Instead, if you walk long enough, something incredible happens. You arrive right back where you started. This is the core idea of a space that is finite but unbounded. The balloon's surface area is obviously finite. You could measure it. And yet, it has no edge. It just curves back on itself. For a 2D creature on this surface, the universe is limited, but you could travel forever and never hit a wall. Your journey would just be one big loop. Now, this analogy is great, but it isn't perfect. First, the balloon's 2D surface is expanding into a 3D space, which can accidentally reinforce that wrong idea of our universe expanding into something. In reality, space can just stretch on its own without needing some extra dimension to expand into. Second, the balloon is made of rubber, while in our universe, it's space itself that's stretching. And finally, the dots are just points. In the real universe, galaxies, solar systems, and people are held together by gravity. The cosmic expansion doesn't make you expand. The dots on the balloon move apart, but the dots themselves don't stretch. Even with those limits, the main concept is what's important. The balloon lets us picture a universe where you can travel in a straight line forever without hitting an edge, all while living in a cosmos that has a finite size. It separates the idea of being finite from being bounded. Our universe could be like the surface of a four-dimensional sphere. Just as the 2D balloon surface curves through a third dimension, our 3D space could curve through a fourth spatial dimension we can't see. If that's the case, a spaceship going in a straight line for an insane amount of time would, shockingly, arrive back at Earth from the opposite direction. It would have literally gone all the way around the universe. This isn't just a fun party trick. It's a real possibility that comes straight out of Einstein's theory of general relativity. It's the ultimate reason you can never fall off the universe. There's nowhere to fall. There's only forward, on a potentially endless loop through space-time. What is the shape of reality? The balloon gives us a great mental picture, but what does the science actually say? What's the true shape of our universe? According to Einstein, the shape of the cosmos is tied to how much stuff matter and energy is in it. All that stuff creates gravity, and gravity warps space-time. This leaves us with three main options for the universe's geometry. First up, a flat universe. Imagine a perfectly flat, infinite sheet of paper. This is the geometry we learned in school, where parallel lines never cross. If the universe is flat, it's almost certainly infinite. There's no edge because it just goes on forever in every direction. If you set off in a spaceship, you'd travel for eternity, always seeing new galaxies, never looping back. All the evidence we have, especially from studying the cosmic microwave background, the Big Bang's afterglow, points to our universe being remarkably, almost perfectly, flat. Data from missions like the Planck satellite shows it's flat to within a tiny margin of error. This leads many cosmologists to believe the whole universe is probably infinite. The second possibility is a closed universe just like our balloon analogy. If the density of the universe is above a certain critical value, gravity would be strong enough to curve space back in on itself, creating a positive curvature. In this universe, space is finite but has no edge. If we lived here, traveling in a straight line would eventually bring you home. So, could we test this? Maybe. If the universe were a finite loop, we might be able to see the same galaxy by looking in opposite directions. So far, we haven't found any evidence for that. For a time, some analyses of the Planck data hinted at a slight curve, sparking a huge debate. However, the general consensus now is that this was likely a statistical blip. The third option is an open universe. If the universe's density is below that critical value, it would have a negative curvature. Think of the shape of a saddle or a Pringles chip. In this kind of universe, space is also infinite and has no edge. Parallel lines would actually curve away from each other. Just like the flat universe, you could travel forever and never return. So, what's the bottom line? In all three of the leading models, flat, closed, or open, there is no edge to fall off of. The universe is either infinite or it's finite and loops back on itself. The question, what's at the edge, is meaningless. There is no edge. Current data strongly favors a flat, infinite universe. But there's a fun little wrinkle. Even if the universe is flat, that doesn't 100% mean it's infinite. It could just be so mind-bogglingly huge that the part we can see looks flat to us, just like a tiny patch of the Earth looks flat to an ant. The universe could still be a giant, closed loop, just one so big that we could never hope to travel all the way around it. It could even have a weirder shape, like a torus, a donut, which is technically flat but would still loop you back to your starting point. No matter which is correct, the answer is the same. The basic structure of space-time just doesn't allow for an edge. But that's just our universe. What if we push this idea even further? Beyond the horizon. The multiverse. Okay, so you can't fall off our universe because it either goes on forever or loops back on itself. But this whole time, we've only been talking about our universe, the one that started with our Big Bang. For a while now, some physicists have been playing with an even more radical idea: the multiverse. And this isn't just sci-fi. Several big, though unproven, theories predict that our universe might just be one bubble in a cosmic ocean of other universes. One of the most popular ideas is called eternal inflation. Inflation theory says that in the first tiny fraction of a second after the Big Bang, the universe blew up at a hyper-accelerated rate. Eternal inflation suggests that this process, once it started, never really stopped. Imagine space as a whole is always expanding. In some spots, like ours, that inflation stopped, letting a stable universe form a bubble. But in the space between these bubbles, inflation rages on, constantly stretching reality and spawning new bubble universes. This would create an infinite cosmic foam of countless universes, each maybe with its own laws of physics. Most would be empty and dead. But with an infinite number to choose from, it's no surprise that some, like ours, would have the right conditions for life. We don't live in a special universe. We just live in one where it's possible for us to exist. Another road to the multiverse comes from the weirdness of quantum mechanics. The many worlds interpretation suggests that every time a quantum event could go one way or another, the universe actually splits. A new, parallel universe is created for every single possible outcome. If this is true, then there's a universe where you chose a different breakfast, a universe where you took that other job, and a universe where the dinosaurs never got wiped out. An infinite number of alternate timelines, branching off at every moment. And this is a huge. But we have to be clear. These are all highly speculative ideas. They are fascinating possibilities that fall out of our current math, but we have absolutely no direct evidence that any other universes exist. Their very nature might make them impossible to detect. Because of this, some scientists argue the multiverse isn't science at all, but philosophy, since it can't be tested. Others hope we might find indirect evidence, like a strange bruise in the cosmic microwave background from an ancient collision with another universe. So far, no luck. Still, the idea is amazing. It takes our concept of an edgeless reality to the extreme. If the multiverse is real, then not only can you not fall off our universe, but our universe itself might just be one edgeless object floating in an infinite sea of other edgeless objects. It suggests a reality where our entire cosmos is just one grain of sand on an infinite beach. Our place in an edgeless cosmos. So, why can you never fall off the universe? The simple answer is that the universe doesn't have an edge to fall off of. Our common sense idea of a boundary just doesn't apply to the whole shebang. We learned that the edge we can actually see, the cosmic horizon, is just a boundary of light and time, the limit of our vision, not the end of existence. Beyond it, there's almost certainly more universe, stretching on and on. We saw, with our balloon, how space could be finite but still have no boundary, looping seamlessly back on itself. And we saw that our best theories say the universe is either infinite or it's finite and closed. In neither case is there an edge. You either travel forever into an endless night, or you travel forever in a giant cosmic loop. Ultimately, the question itself is the problem. It comes from our everyday experience where everything has an edge. Rooms have walls, islands have shores. But the universe isn't an object in a bigger space. The universe is the space. It's the totality of everything. There can be no outside, because if there were, we'd just call that part of the universe, too. Standing under a clear night sky, it's natural to wonder, how big is it? And where does it end? What science gives us is an answer far stranger and more beautiful than we could have imagined. It hasn't given us a map with a border. It has erased the border entirely, leaving us with the dizzying possibilities of infinity, endless loops, and maybe, just maybe, countless other worlds. We aren't standing on a cosmic ledge. We are woven into the very fabric of a reality that may have no end at all. If your brain enjoys being twisted into a pretzel by questions like these, make sure to subscribe and hit that notification bell. We dive into the biggest ideas in science every week. And let us know in the comments. What does the idea of an edgeless, infinite, or looping universe make you feel? A little freaked out? Let's talk about it. Thanks for watching.